Hello there, and welcome to Sleep Science Chronicles. Tonight, we turn our attention to something so familiar it often escapes our notice, yet so extraordinary that it has puzzled the greatest minds in history. We are going to explore light, the soft glow of a candle, the warmth of the sun on your face, the colors of a sunset spreading across the evening sky. Light is woven into every moment of our waking lives, and yet its true nature remains one of the most beautiful mysteries science has ever tried to understand. This evening, we will travel from the heart of stars to the back of your eye, from the smallest particles physicists have ever measured to the vast distances between galaxies. We will discover how light bends and bounces, how it paints the sky in colors, how it lets us see the past when we look at the stars, and how life itself learned to capture its energy and glow in the darkness of the deep sea. Some of what we explore will be gentle and intuitive, like the way a prism spreads white light into a rainbow. Other ideas will be stranger, like the fact that light is both a wave and a particle at the same time, or that nothing in the universe can ever travel faster than it does. But all of it will unfold slowly, calmly, one quiet discovery at a time. You do not need to remember any of this. You do not need to take notes or stay focused. Let the words drift past you like light itself, touching gently and moving on. If sleep finds you along the way, that is perfectly fine. The story will continue softly in the background, and the light will still be there when you wake. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, let your breath slow and your thoughts soften. Let us begin. Light is one of the most fundamental things in the universe, and yet defining exactly what it is took humanity thousands of years. The ancient Greeks believed that vision worked because our eyes sent out invisible rays that touched the objects around us and returned with information. It was a reasonable guess, but it was backwards. Light does not come from our eyes. It comes from everything that shines, glows, burns, or reflects. And our eyes are simply receivers, gathering what arrives. For most of history, light was thought to be instantaneous. When you opened your eyes, there it was. When you lit a candle, the room filled with brightness all at once. The idea that light might take time to travel seemed absurd. What could possibly slow it down? It moved through air, through glass, through the emptiness of space. It seemed to exist everywhere at once, connecting the eye to the world in a single unbroken moment. But light does travel, and it travels at a speed so fast it is almost impossible to comprehend. In 1 second, a beam of light crosses nearly 300,000 kilometers. That is fast enough to circle the Earth more than 7 times in the span of a single heartbeat. Fast enough to reach the moon in just over a second. Fast enough that when you look at the sun, you are seeing it as it was 8 minutes ago, because that is how long its light takes to reach you. Light is made of tiny packets of energy called photons. A photon has no mass. It weighs nothing at all. And yet it carries energy, momentum, and information across the vast distances of space. When you see a star twinkling in the night sky, what you are really seeing is a stream of photons that left that star years, decades, or even centuries ago, traveling silently through the void until they finally arrived at your eye. Each photon is born in a moment of energy release. When an atom gets excited, when electrons jump between energy levels, when matter heats up or particles collide. Photons are created and sent out into the world. Some travel only a tiny distance before being absorbed again. Others cross the entire observable universe, carrying with them the signature of the moment they were born. One of the strangest things about light is that it behaves like two completely different things at the same time. In some experiments, light acts like a wave. It ripples. It spreads out. It creates patterns of interference where crests and troughs overlap. You can see this when light passes through a narrow slit and fans out on the other side, or when two beams of light cross and create bands of brightness and darkness. But in other experiments, light acts like a particle. It arrives in discrete packets. It can knock electrons loose from metal surfaces one photon at a time. It can be counted, detected, and measured as individual units of energy. This dual nature is not a trick or an illusion. It is a fundamental feature of reality. Light is both a wave and a particle depending on how you choose to observe it. This discovery shook the foundations of physics in the early 20th century. Scientists had spent centuries arguing about whether light was made of waves or particles, and the answer turned out to be both. The same beam of light that ripples like water through a double slit will also strike a detector as a series of individual hits, each one a single photon arriving at a single point. The wave nature of light is described by its wavelength and frequency. Wavelength is the distance between one crest of the wave and the next. Frequency is how many crests pass a given point in 1 second. These two properties are intimately connected. The shorter the wavelength, the higher the frequency. The longer the wavelength, the lower the frequency. And both together determine the energy of the photon. High-frequency light carries more energy. Low-frequency light carries less. The light we can see, the light that paints the world in color, occupies only a tiny sliver of all the wavelengths that exist. This visible spectrum stretches from about 400 nanometers at the violet end to about 700 nanometers at the red end. A nanometer is 1/billionth of a meter, unimaginably small. And within that narrow band, every color you have ever seen finds its place. Beyond the violet end lies ultraviolet light, invisible to our eyes, but felt by our skin as sunburn. Beyond that lies X-rays, and beyond those, gamma rays, the most energetic photons in the universe. On the other side of the spectrum, past the red end, lies infrared light, which we feel as heat. Beyond that lies microwaves, and beyond those, radio waves, stretching out to wavelengths longer than buildings, longer than mountains, longer than cities. All of these are light. They are all made of photons. They all travel at the same speed through empty space. The only difference is their wavelength and frequency. And that difference determines everything about how they interact with matter. Radio waves pass through walls. X-rays pass through flesh, but not bone. Visible light bounces off most surfaces, which is why you can see those surfaces. Each type of light has its own way of moving through the world. The speed of light in a vacuum is exactly 299,792,458 meters per second. Scientists know this number with extraordinary precision because it has been measured countless times with increasingly accurate instruments. In fact, the speed of light is now used to define the meter itself. 1 meter is the distance light travels in a vacuum in 1,299,792,458th of a second. This speed is not just fast. It is the fastest anything can ever go. According to Einstein's theory of special relativity, nothing with mass can ever reach the speed of light. As an object speeds up, it gains energy, and that energy adds to its effective mass, making it harder to accelerate further. The closer you get to the speed of light, the more energy you need to go even a tiny bit faster. To actually reach light speed would require infinite energy, which is impossible. Only massless particles like photons can travel at the speed of light. And they do not just travel at that speed sometimes. They always travel at that speed, in every frame of reference. This leads to some of the strangest consequences in physics. Time slows down for objects moving close to the speed of light. Distances contract. Events that seem simultaneous to one observer happen at different times for another. Light speed is not just a limit. It is a fundamental constant that shapes the geometry of space and time. When light enters a material like water or glass, it slows down. In water, light travels at about 75% of its vacuum speed. In glass, it slows to about 65%. In diamond, it drops to just 40% of its maximum velocity. This slowing is what causes light to bend when it crosses from one material to another, a phenomenon called refraction. Refraction is why a straw in a glass of water looks bent at the surface. It is why lenses can focus light to a point. It is why your eyes work at all, bending incoming rays so they converge on your retina. Every time light crosses a boundary between materials with different optical properties, it changes direction slightly. And that bending is the basis for all of optics, from microscopes to telescopes to the glasses on your face. The amount of bending depends on the wavelength of the light. Shorter wavelengths bend more than longer ones. This is why a prism can spread white light into a rainbow. The white light enters the prism as a mixture of all visible wavelengths. Each wavelength bends by a slightly different amount. By the time the light exits the other side, the colors have separated, fanning out into a spectrum from violet to red. Isaac Newton was the first to demonstrate this systematically, passing sunlight through a prism and showing that white light was not pure but composite. He then passed the separated colors through a second prism and showed that they did not break down further. Each color was fundamental. The rainbow was hidden inside the light all along, waiting to be revealed. Light travels in straight lines through uniform materials. This is why shadows have sharp edges and why you cannot see around corners. When light encounters an obstacle, it does not curve around it the way sound does. It stops, blocked by the object, leaving a dark region behind. The edge of the shadow marks the boundary between light and darkness, the limit of where photons can reach. But this straightness is only approximate. At very small scales, light does bend around edges. This is called diffraction, and it happens because of light's wave nature. When a wave passes through a narrow opening or around a sharp corner, it spreads out slightly. The narrower the opening, the more the spreading. This is why the sharpness of shadows depends on the size of the light source and the distance to the surface. A point source of light casts sharp shadows. A broad source casts soft ones with fuzzy edges. Diffraction also creates beautiful patterns when light passes through very small openings or around very fine structures. The colors on a soap bubble, the shimmer on a compact disc, the iridescence of a butterfly wing, all of these arise from diffraction and the interference of light waves with each other. When crests meet crests, the light gets brighter. When crests meet troughs, the light cancels out. The result is a complex pattern of colors that shifts and changes as you move. The sun is the source of almost all the light on Earth. Deep in its core, where temperatures reach 15 million degrees and pressures are unimaginably intense, hydrogen atoms are fused into helium, and a tiny fraction of their mass is converted into energy. That energy takes the form of gamma rays, the most energetic photons in existence, born in the heart of the sun and beginning a long journey outward. But those gamma rays do not travel in a straight line. The sun's interior is so dense that photons cannot move more than a fraction of a millimeter before they are absorbed and re-emitted by another particle. Each absorption and re-emission sends the photon in a random direction. The result is a slow, wandering path, a random walk that takes an astonishingly long time. Estimates vary, but it may take a photon anywhere from 10,000 to 170,000 years to travel from the core to the surface of the sun. By the time that energy reaches the surface, it has been transformed. The countless absorptions and re-emissions have stretched the wavelengths, lowered the energies. What began as gamma rays emerge as visible light, infrared radiation, and ultraviolet rays. The sun glows not because its surface is as hot as its core, but because the energy released in fusion has finally found its way out, changed, but undiminished. The surface of the sun, called the photosphere, has a temperature of about 5,500 degrees Celsius. That temperature determines the color of the light the sun emits. Hotter stars burn blue or white. Cooler stars glow orange or red. Our sun sits in the middle, producing a yellowish-white light that peaks in the green part of the spectrum. The reason we do not see the sun as green is that it emits all visible wavelengths strongly, and our eyes perceive this mixture as white. Once sunlight leaves the surface, it travels unimpeded through the vacuum of space. 8 minutes and 20 seconds later, it reaches Earth. Some of that light is reflected back into space by clouds and ice. Some is absorbed by the atmosphere, and some makes it all the way to the surface, warming the land and sea, powering photosynthesis, and making vision possible. The atmosphere scatters sunlight in all directions. When light encounters tiny molecules of nitrogen and oxygen, some of it bounces off at random angles. Shorter wavelengths scatter more than longer ones. Blue light scatters the most, which is why the sky appears blue during the day. The blue you see overhead is sunlight that has been redirected toward your eyes by countless collisions with air molecules. At sunrise and sunset, sunlight has to pass through more of the atmosphere to reach you. The longer path means more scattering, and by the time the light arrives, most of the blue has been scattered away. What remains is the longer wavelengths, the oranges and reds that paint the sky in those warm, gentle colors we associate with the beginning and end of day. Sometimes when conditions are just right, the sky at twilight takes on shades of purple and pink. This happens when the light has been scattered multiple times, when the upper atmosphere catches rays that have already been filtered and redirected. The colors mix in ways that no single scattering event could produce, creating gradients of extraordinary beauty that shift from moment to moment as the sun sinks below the horizon. The human eye is a remarkable instrument, shaped by hundreds of millions of years of evolution to detect light and convert it into signals the brain can interpret. Light enters through the cornea, the clear outer layer, which begins the process of focusing. It passes through the pupil, the opening at the center of the iris, which expands and contracts to control how much light gets in. Then it passes through the lens, which fine-tunes the focus, bending the rays so they converge on the retina at the back of the eye. The retina is where the magic happens. It is lined with millions of photoreceptor cells, specialized neurons that respond to light. There are two main types. Rods are sensitive to dim light and motion, but do not detect color. They are most abundant around the edges of the retina and allow you to see in low light conditions. Cones are responsible for color vision and fine detail. They are concentrated in the center of the retina, in a region called the fovea, and they need brighter light to function. Humans have 3 types of cones, each sensitive to a different range of wavelengths. One type responds most strongly to long wavelengths, which we perceive as red. Another responds to medium wavelengths, which we perceive as green. The third responds to short wavelengths, which we perceive as blue. Every color you see is the result of your brain combining the signals from these 3 cone types in different proportions. This is why we call the primary colors of light red, green, and blue. By mixing these 3 in various intensities, it is possible to create the perception of almost any color. Your television screen, your phone screen, every digital display works on this principle. Tiny clusters of red, green, and blue light sources, too small to see individually, combine to produce the full spectrum of visible color. The color of an object depends on which wavelengths of light it reflects. A red apple absorbs most wavelengths, but reflects red light back to your eye. A green leaf reflects green and absorbs the rest. A white surface reflects all wavelengths equally, while a black surface absorbs almost everything. The colors we see are not properties of the objects themselves, but of the light they send to our eyes. This means that color is not entirely objective. It depends on the light source, the surface, and the observer. Under different lighting conditions, the same object can appear to change color. A shirt that looks blue in daylight might look purple under incandescent bulbs. A piece of fruit that looks appetizing in the market might look dull and unappealing under fluorescent lights. Our perception of color is a construction, a story the brain tells based on incomplete information. The brain does remarkable work to keep colors stable despite changing lighting. This is called color constancy. When you walk from a sunny room into a shadowy hallway, the wavelengths reaching your eyes change dramatically. Yet the colors of objects seem to remain mostly the same. Your brain adjusts for the difference, compensating for the shift in illumination to present a consistent picture of the world. Some people are born with color vision deficiencies, commonly called color blindness. The most frequent form involves difficulty distinguishing red from green, caused by a missing or altered cone type. About 8% of men and 0.5% of women have some form of color vision deficiency. For them, certain colors that look distinct to most people appear nearly identical. At the other extreme, a small number of people may have 4 types of cones instead of 3. This condition, called tetrachromacy, could theoretically allow perception of colors invisible to the rest of us. Subtle distinctions in the yellow and orange range that trichromats cannot detect. Research on tetrachromacy is still ongoing, and its prevalence and practical effects remain subjects of scientific investigation. Animals perceive light in wildly different ways. Bees can see ultraviolet light, which reveals patterns on flowers invisible to human eyes, guiding them to nectar. Many birds have 4 types of cones, giving them access to a broader spectrum than we enjoy. Mantis shrimp have 16 types of photoreceptors, though scientists believe this does not give them better color vision, but rather faster color recognition, useful for their rapid predatory strikes. Some animals have eyes adapted for extreme low light. Owls have enormous eyes relative to their body size, with pupils that can open wide to gather every available photon. Deep-sea fish have developed eyes so sensitive they can detect the faint glow of bioluminescence in the darkness of the abyss. Cats have a reflective layer behind their retinas called the tapetum lucidum, which bounces light back through the photoreceptors, effectively giving them a second chance to detect each photon. The pit viper has specialized organs that detect infrared light, allowing it to sense the body heat of warm-blooded prey in total darkness. These pit organs are so sensitive they can detect temperature differences of a fraction of a degree, creating a thermal image of the world that overlays the snake's regular vision. For the viper, light is not just visible wavelengths, but heat itself, a glow that betrays the presence of living things. Light carries information, and humans have learned to read that information in extraordinary detail. Spectroscopy is the science of splitting light into its component wavelengths and analyzing the resulting spectrum. Every element, when heated, emits light at specific wavelengths, a unique fingerprint of bright lines against a dark background. By examining the light from a distant star, astronomers can determine what elements are present, how hot the star is, how fast it is moving, and even whether it has planets. When a star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the shift is toward the red. This is called the Doppler effect, and it works for light just as it works for sound. By measuring these shifts, scientists can track the motion of stars and galaxies across the cosmos. The discovery that almost all distant galaxies are redshifted, moving away from us, was key evidence that the universe is expanding. Light also bends when it passes close to massive objects. This is one of the predictions of general relativity, Einstein's theory of gravity. Mass warps the fabric of space-time, and light follows the curves in that fabric. When light from a distant galaxy passes near a massive cluster of galaxies, it can be bent so strongly that the distant galaxy appears magnified or distorted. Sometimes a single galaxy appears as multiple images, its light taking different paths around the gravitational lens. The first confirmation of this effect came in 1919 during a solar eclipse. Astronomers measured the positions of stars near the sun and found they were slightly shifted from their usual places. The sun's gravity was bending the starlight, displacing the apparent positions of the stars. This result made Einstein famous and confirmed that gravity affects light just as it affects matter. Light can also be polarized, meaning its waves oscillate in a particular direction. Unpolarized light vibrates in all directions perpendicular to its path. Polarized light vibrates in just one plane. Polarizing filters block all light except that which vibrates in a specific direction, which is why polarized sunglasses can reduce glare from reflective surfaces like water or glass. The reflected light is partially polarized, and the filter removes it, leaving a clearer view. Some animals can see polarized light, which gives them navigational advantages. Bees use the polarization patterns in the sky to orient themselves even when the sun is hidden by clouds. Certain marine creatures use polarized light to communicate in ways invisible to predators. The ability to detect polarization opens up an entire dimension of visual information that most humans never perceive. Light exerts pressure. When photons strike a surface, they transfer a tiny amount of momentum, pushing against the surface ever so slightly. This radiation pressure is incredibly weak under ordinary circumstances, far too faint to feel. But in space, where there is no air resistance and objects can accelerate over long periods, light pressure becomes significant. Solar sails are spacecraft propelled by radiation pressure. They unfurl enormous reflective surfaces, and the pressure of sunlight pushes them gradually faster and faster. No fuel is required, just the steady push of photons from the sun. The acceleration is slow, but over months and years it adds up, and solar sails can reach speeds far beyond what conventional rockets could achieve for the same mission. At the other extreme, the pressure of light inside massive stars helps hold them up against gravitational collapse. The energy generated by fusion creates an outward push that balances the inward pull of gravity. When a star exhausts its fuel and the light pressure drops, gravity wins and the star collapses, often triggering a supernova explosion. The night sky is filled with ancient light. When you look at the stars, you are looking back in time. The light from the nearest star beyond the Sun, Proxima Centauri, takes about 4 years to reach us. The light from Sirius, the brightest star in our sky, has been traveling for nearly 9 years. The light from Betelgeuse, the red supergiant in Orion's shoulder, left that star around 600 years ago, when the Renaissance was just beginning on Earth. The Andromeda Galaxy, the most distant object visible to the naked eye, is about 2.5 million light-years away. The light entering your eyes from Andromeda began its journey before modern humans existed, before our ancestors had left Africa, before the genus Homo had even evolved. You are seeing Andromeda not as it is, but as it was in an unimaginably distant past. With powerful telescopes, astronomers can see even further back. The most distant galaxies detected are more than 13 billion light-years away. Their light has been traveling since shortly after the Big Bang, when the universe was young and the first stars were just beginning to form. Looking at these galaxies is like looking through a window into the infancy of the cosmos. The oldest light of all is the cosmic microwave background, a faint glow that fills the entire sky. This light was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely for the first time. Before that moment, the universe was an opaque fog of particles. After that moment, it became transparent. The light released in that transition has been traveling ever since, stretched by the expansion of the universe from visible light into microwaves. When we map the cosmic microwave background, we see tiny variations in temperature, differences of only a few hundred thousandths of a degree. These variations are the seeds of all the structure we see today. Slightly denser regions pulled in more matter over billions of years, becoming galaxies and galaxy clusters. Slightly less dense regions became the voids between them. The pattern of light in the cosmic microwave background is like a baby picture of the universe, showing the initial conditions from which everything grew. Light is essential to life on Earth in ways that go far beyond vision. Photosynthesis, the process by which plants and certain bacteria convert sunlight into chemical energy, is the foundation of almost every food chain on the planet. Chlorophyll molecules absorb red and blue light, using that energy to split water molecules and build sugars from carbon dioxide. The oxygen we breathe is a byproduct of this process, released as waste by photosynthesizing organisms. Without photosynthesis, there would be no oxygen in the atmosphere. Without light, there would be no photosynthesis. The air you are breathing right now, the food you ate today, the warmth of your body, all of it traces back to sunlight captured by green things and transformed into forms that sustain the rest of life. Light also regulates our internal clocks. The human body has a circadian rhythm, a roughly 24-hour cycle that governs sleep, hormone release, body temperature, and many other processes. This rhythm is synchronized to the day-night cycle by light entering the eyes. Specialized cells in the retina, different from the rods and cones used for vision, detect light levels and send signals to a small region of the brain called the suprachiasmatic nucleus, which acts as the body's master clock. Exposure to bright light in the morning helps reset the circadian rhythm, making you feel alert and awake. Exposure to light at night, especially blue-rich light from screens, can delay the rhythm, making it harder to fall asleep. The sleep difficulties many people experience in the modern world are partly due to our exposure to artificial light at times when our ancestors would have been in darkness. Before electric lights, humans lived by the rhythms of the sun. Days began at dawn and ended at dusk. Firelight and candles provided some illumination after dark, but nothing like the brightness we take for granted today. The invention of the incandescent bulb in the late 19th century transformed human society, extending the productive day, enabling night shifts, changing the very structure of work and leisure. Today, artificial light is so pervasive that most people in developed countries have never experienced true darkness. Light pollution washes out the stars, turning the night sky into a featureless glow. In many cities, you can count the visible stars on one hand. The Milky Way, once a familiar sight to every human who looked up at night, has become invisible to a third of humanity. And yet, even in the brightest cities, light continues to arrive from the cosmos. Photons that have traveled billions of years still rain down on Earth, mixing with the glare of street lamps and neon signs. The universe is always speaking to us in light, if only we have the means and the patience to listen. The study of light has driven some of the greatest revolutions in physics. The nature of light was central to the development of quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales. When physicists tried to understand why hot objects glow the way they do, they discovered that energy is not continuous, but comes in discrete packets. Those packets are photons, and their discovery opened the door to a new understanding of reality. Quantum mechanics reveals that light is far stranger than everyday experience suggests. A single photon can interfere with itself, passing through two slits at once and creating a pattern as if it were a wave. But if you try to determine which slit it went through, the pattern disappears and the photon behaves like a particle. The act of observation changes the outcome. Reality at the quantum level is not fixed until it is measured. This is not a failure of our instruments or our understanding. It is a fundamental feature of the universe. Light does not have a definite position or path until it is detected. Until then, it exists in a superposition of possibilities, a cloud of potential outcomes that collapses into a single reality only when observed. The implications of this have puzzled physicists for a century and continue to inspire debate and wonder. Entanglement is another strange property of light. Two photons can be created in such a way that their properties are correlated no matter how far apart they travel. Measure the polarization of one photon, and you instantly know the polarization of the other, even if it is on the other side of the galaxy. This does not allow faster-than-light communication, but it does suggest that the universe is more deeply connected than our everyday intuitions would lead us to believe. Lasers are a modern technology that exploits the quantum properties of light. A laser produces light that is coherent, meaning all the photons have the same wavelength and are in phase with each other. This coherence gives laser light its special properties. It can be focused to an incredibly tiny point. It can travel long distances without spreading, and it can carry information with extraordinary precision. Lasers are used in barcode scanners and laser pointers, in fiber optic communications and surgical tools. They read the data on CDs and DVDs. They measure distances with extraordinary accuracy, from the gap between components in a computer chip to the distance between the Earth and the Moon. Laser light is one of the most versatile tools humanity has ever developed, and it all comes from our understanding of how photons behave. Fiber optic cables carry light signals across continents and under oceans, transmitting the vast majority of the world's internet traffic. Inside each cable, thin strands of glass guide light through total internal reflection, bouncing it along the fiber with almost no loss. A single fiber can carry trillions of bits of information per second, and cables containing hundreds of fibers link the digital world together. The pulses of light racing through these fibers encode everything from emails to video calls, financial transactions, to scientific data. When you send a message to someone on another continent, your words are converted into patterns of light, shot through glass at the speed of light, and reassembled into words on the other end. The global communication network is, at its heart, a system of light. Light is also used to cool things down. It seems counterintuitive since we associate light with warmth, but carefully tuned lasers can slow atoms to a near standstill, bringing them to temperatures just a fraction of a degree above absolute zero. This technique, called laser cooling, works by using the momentum of photons to slow the motion of atoms, removing energy bit by bit until the atoms barely move at all. At these extreme low temperatures, matter behaves in strange ways. Atoms can form a new state of matter called a Bose-Einstein condensate, where they lose their individual identities and act as a single quantum entity. Laser cooling has enabled some of the most precise measurements ever made, including atomic clocks accurate to within a second over billions of years. Light carries not just energy, but also angular momentum. Photons can spin, and that spin can be transferred to matter. Specialized beams of light called optical vortices carry orbital angular momentum, spiraling as they travel. These beams can rotate tiny particles, acting as optical tweezers that grip and manipulate objects far too small to see with the naked eye. Optical tweezers have revolutionized biology and medicine. Researchers use them to move individual cells, to stretch DNA molecules, to measure the forces exerted by molecular motors. What once seemed like science fiction, using light to pick up and move physical objects, is now a routine laboratory technique. The human experience of light is rich with emotion and meaning. We speak of enlightenment and illumination, of seeing the light and being left in the dark. Light is associated with knowledge, goodness, and hope. Darkness is associated with ignorance, danger, and fear. These associations run deep, shaped by millions of years of evolution in a world where daylight meant safety and night brought predators. Festivals of light appear in cultures around the world. Diwali, Hanukkah, Christmas, and the winter solstice celebrations of many traditions all involve the kindling of lights against the darkness. These festivals often fall near the shortest days of the year, when the sun's absence is most keenly felt, and the return of light becomes a symbol of renewal and hope. Artists have long been fascinated by light. The Impressionists painted light itself, capturing the way it fell on water and stone, the way it shifted through the day, the way it transformed ordinary scenes into shimmering visions. Photographers speak of the golden hour, the time just after sunrise or before sunset, when the light is warm and soft, perfect for capturing beauty. Filmmakers use light to set mood, to guide attention, to tell stories without words. In the quiet of this evening, as these words drift past you, light continues its endless journey. Somewhere, a photon born in a distant star is just now arriving at Earth, completing a voyage of centuries or millennia. Somewhere else, sunlight is filtering through the leaves of a forest, dappling the ground with patterns of shadow and gold. In your room, the soft glow of whatever light source illuminates your space is filling the air with photons, bouncing off every surface, carrying information about color and shape to anyone with eyes to see. You are surrounded by light even in the dimmest room. The warmth of your body emits infrared radiation, invisible but real. The atoms in the walls around you vibrate and glow faintly in wavelengths far beyond what your eyes can detect. The universe is never truly dark. It is filled with light in all its forms, a symphony of photons playing across every scale, from the quantum to the cosmic. And so, as you rest, know that light is with you. The same light that powers the sun, that paints the sky, that lets you see the faces of those you love. It asks nothing of you. It simply is, traveling at the speed of the universe's fastest constant, connecting everything to everything, the silent messenger of the cosmos. Let your eyes grow heavy if they wish. Let your thoughts drift like light through empty space, following no particular path, carrying no particular burden. The universe will continue its luminous unfolding whether you watch or not. And in the morning, when you open your eyes, the light will still be there, faithful and unchanged, ready to show you the world once more. The visible spectrum is a rainbow compressed into a sliver so narrow, it seems almost miraculous that we can see it at all. Out of all the possible wavelengths of electromagnetic radiation, stretching from gamma rays smaller than atoms to radio waves longer than mountains, our eyes respond to a band only a few hundred nanometers wide. And yet, within that band lies every sunset, every forest, every face, every color that has ever moved a human heart. Red light has the longest wavelength we can see, around 700 nanometers. It carries the least energy of the visible photons, and it scatters the least in the atmosphere, which is why red remains visible at sunset when blue has long since scattered away. Red is the color of fire and blood, of warning signs and ripe fruit. It draws the eye, demanding attention. Orange follows, a blend of red's warmth with the brightness of yellow. It is the color of autumn leaves, of citrus fruit, of embers glowing in a dying fire. Orange light has slightly more energy than red, slightly shorter wavelengths, occupying a narrow band in the spectrum that our eyes perceive as its own distinct hue. Yellow is brighter still, the color of sunlight itself when filtered through atmosphere, the color of gold and butter and daffodils. Yellow wavelengths are shorter than orange, around 570 to 590 nanometers. Curiously, our eyes are most sensitive to light in the yellow-green part of the spectrum, which is why emergency signs and highlighters often use these colors. Green occupies the center of the visible spectrum, around 500 to 560 nanometers. It is the color of chlorophyll, the molecule that captures sunlight and makes life possible. Forests and fields and algae-rich waters all glow green because chlorophyll reflects these wavelengths while absorbing red and blue for photosynthesis. Green is the color of growth, of spring, of living things. Blue light has shorter wavelengths than green, around 450 to 495 nanometers. It carries more energy, scatters more easily in the atmosphere, and gives the sky its characteristic color. Blue is the color of water and ice, of distance and depth. When you look at a mountain far away, it appears bluish because the intervening air scatters blue light toward your eyes. Violet lies at the edge of human vision, with wavelengths between 380 and 450 nanometers. It is the highest energy visible light, teetering on the boundary of the ultraviolet. Some people can see slightly into the ultraviolet range, particularly after cataract surgery removes the lens that normally blocks these wavelengths. For them, the world contains colors the rest of us cannot perceive. Between these named colors lie infinite gradations. The spectrum is continuous, not divided into neat boxes. Our color words are approximate, attempts to categorize a smooth gradient with discrete labels. Different languages divide the spectrum differently, and speakers of those languages perceive colors differently as a result. The boundaries between blue and green, or red and orange, are cultural as much as physical. White light is a mixture of all visible wavelengths in roughly equal proportions. When sunlight passes through a prism and fans out into a rainbow, the white is revealed to be a combination, a chord of color struck all at once. Our eyes perceive this mixture as colorless, as pure as the absence of tint. But white is not simple. It is complex, a harmony of every hue. Black is the absence of light, or more precisely, the absence of light reaching our eyes. A black object absorbs nearly all wavelengths, converting their energy into heat rather than reflecting it back. In a perfectly dark room, there are no photons to stimulate your retinas, and you see nothing at all. Yet even then, faint flashes of light may appear, generated by random noise in your visual system, reminders that perception is always an active process. Gray lies between white and black, a partial reflection of all wavelengths. A gray surface reflects some light, but not all, sending a diminished version of the incoming illumination back to your eye. The infinite shades of gray between pure white and pure black allow us to perceive depth, texture, and form even in photographs stripped of color. The colors we see depend not only on the wavelengths present, but on the context in which we see them. A patch of gray can appear lighter or darker depending on what surrounds it. A color can shift toward its complement when placed next to a strong hue. Our perception of color is relational, shaped by comparison, always interpreting rather than simply recording. This is why color matching is so difficult. The paint that looks perfect in the store may look completely different on your wall, under different lighting, against different surroundings. The dress that sparked an internet debate appeared blue and black to some viewers, white and gold to others, because their brains made different assumptions about the illumination. Color is not an objective property of surfaces, but a construction of the mind. The light around us comes from many sources, each with its own spectrum. Sunlight is broad, containing all visible wavelengths in relatively even proportions. Incandescent bulbs produce light by heating a filament until it glows, emitting a warm spectrum rich in red and yellow, but weaker in blue. Fluorescent lights work by exciting gases that emit specific wavelengths, often giving a cooler, bluer cast. LEDs can be tuned to produce almost any spectrum, from warm tones that mimic incandescent bulbs to cool blue-white light for task lighting. The ability to control the spectrum of artificial light has transformed interior design, photography, and even our health. As we learn more about how different wavelengths affect our circadian rhythms and mood. The color temperature of light is measured in kelvins, a scale that describes the hue of light emitted by an idealized black body at a given temperature. A candle flame has a color temperature around 1,800 kelvins, warm and orange. An incandescent bulb is around 2,700 kelvins. Noon sunlight is about 5,500 kelvins. An overcast sky can reach 6,500 kelvins or higher, taking on a bluish cast. This scale seems backwards at first. Higher temperatures correspond to cooler, bluer colors, while lower temperatures give warmer, redder hues. But it makes sense physically. As an object heats up, it first glows red, then orange, then yellow, then white, then blue-white. The hottest stars are blue. The coolest are red. Temperature and color are intimately linked in the physics of thermal radiation. Our ancestors knew none of this, yet they lived their lives by light. They watched the sun cross the sky and marked the seasons by its changing angle. They told time by shadows and navigated by stars. They gathered around fires at night, their faces lit by the same orange glow that had comforted humanity for hundreds of thousands of years. Light was life itself, the difference between safety and danger, warmth and cold, vision and blindness. Tonight, as you rest in whatever light surrounds you, you are continuing a relationship that stretches back to the dawn of life on Earth. The first single-celled organisms evolved light-sensitive proteins billions of years ago, simple molecules that could detect the presence or absence of illumination. Over eons, those proteins evolved into eyes, and eyes evolved into the extraordinary organs you use to read these words or watch this screen. Light has shaped evolution in countless ways. Flowers evolved bright colors to attract pollinators that could see them. Prey animals evolved camouflage to blend into their surroundings and escape notice. Predators evolved keen vision to spot their prey against confusing backgrounds. The entire visible world is a product of the evolutionary arms race between seeing and being seen. Even the human face evolved partly in response to light. The whites of our eyes, larger than in any other primate, may have evolved to help others see where we are looking, facilitating social communication in a species that relies heavily on cooperation. The blush of embarrassment and the pallor of fear are visible because our skin transmits light, revealing changes in blood flow that signal our emotional state. Light is information. It carries messages across space, from the sun to the earth, from stars to our telescopes, from screens to our eyes. It encodes data in the pulses racing through fiber optic cables and the radio waves bouncing between satellites. The universe is a vast network of information exchange, and light is its primary language. As you breathe slowly and let your muscles relax, remember that you are part of this luminous web. Photons from the sun are striking your window or your wall. Photons from your lamp or your screen are entering your eyes. Photons from your own warm body are radiating outward into the room. You are both a receiver and a sender of light, a node in the cosmic network, bathed in the same radiation that fills the universe. There is no need to hold on to any of this. Let the facts drift past like light through a prism, separating for a moment into colors, then blending again into the soft glow of rest. The universe will keep its secrets and its wonders, whether you remember them or not. What matters now is only this: the quiet, the warmth, the gentle presence of light, and the slow approach of sleep. When light crosses from one material into another, something beautiful happens. It bends. A beam of light traveling through air enters water at an angle, and instead of continuing in a straight line, it changes direction, tilting toward an invisible line perpendicular to the surface. This bending is called refraction, and it is one of the most important phenomena in all of optics. The reason light bends is that it travels at different speeds in different materials. In a vacuum, light moves at its maximum speed, nearly 300,000 kilometers per second. In air, it slows down by a tiny fraction, hardly noticeable. In water, it slows to about 75% of its vacuum speed. In glass, it slows to around 65%. In diamond, it drops to just 41% of its maximum velocity. When light enters a slower medium at an angle, one side of the wavefront slows down before the other. Imagine a line of people walking arm in arm across a field, then stepping onto a muddy patch. The first person to hit the mud slows down, while the others are still on solid ground. The line pivots, changing direction. Light does the same thing, its wavefront bending as different parts enter the new medium at different times. The amount of bending depends on the ratio of speeds in the two materials, a property called the refractive index. Air has a refractive index of about 1.0003, very close to a vacuum. Water has a refractive index of about 1.33. Glass varies depending on its composition, but typically falls between 1.5 and 1.9. Diamond has one of the highest refractive indices of any natural material, around 2.42, which is why diamonds sparkle so brilliantly. The higher the refractive index, the more light slows down, and the more it bends when entering at an angle. This is why diamond cutters carefully calculate angles to maximize internal reflections, trapping light inside the gem and releasing it in flashes of color. A well-cut diamond bends and bounces light so effectively that it seems to glow from within. Refraction explains why a straw in a glass of water appears bent or broken at the surface. Light from the submerged part of the straw bends as it exits the water and enters the air, shifting the apparent position of the straw. Your brain interprets the light as traveling in straight lines, so it perceives the straw as displaced from its true location. The same effect makes pools appear shallower than they are. Light from the bottom of the pool bends as it exits the water, making the bottom seem closer to the surface. Swimmers sometimes misjudge depths because of this illusion. The water is always deeper than it looks. Refraction also creates mirages. On a hot day, the air near the ground becomes less dense than the air above it. This creates a gradient in refractive index, with light traveling faster near the hot surface. Light from the sky curves upward as it passes through this gradient, creating the illusion of water on the road ahead. What you see is actually an image of the sky, bent by the atmosphere and projected onto the ground. In deserts, mirages can be elaborate and deceptive. Distant objects may appear to float above the ground, separated from their true positions by shimmering bands of displaced air. Travelers have mistaken these illusions for oases, lakes, and cities, chasing phantoms created by nothing more than temperature differences in the air. The opposite effect, called a superior mirage, occurs when cold air lies beneath warmer air. In this case, light curves downward, and distant objects may appear elevated or stretched vertically. Ships beyond the horizon can become visible, lifted into view by the bending of light. The phenomenon known as Fata Morgana, named after the sorceress of Arthurian legend, produces complex, rapidly changing mirages of cliffs, towers, and walls that seem to rise from the sea. Lenses work by using refraction to focus light. A convex lens, thicker in the middle than at the edges, bends incoming rays so they converge at a point called the focal point. This is how magnifying glasses concentrate sunlight to start fires, how cameras focus images onto sensors, and how your eyes focus the world onto your retinas. A concave lens, thinner in the middle than at the edges, does the opposite. It spreads light rays apart, causing them to diverge as if they came from a virtual focal point behind the lens. Concave lenses are used to correct nearsightedness, spreading light so it focuses correctly on retinas that would otherwise focus images in front of themselves. The human eye contains a natural lens made of transparent, flexible tissue. Muscles surrounding the lens can change its shape, adjusting its curvature to focus on objects at different distances. When you look at something close, the lens thickens, bending light more sharply. When you look at something far away, the lens flattens, bending light less. This automatic adjustment, called accommodation, happens so smoothly that you never notice it. As people age, the lens becomes less flexible, making it harder to focus on close objects. This is why many people need reading glasses in middle age, even if they had perfect vision before. The lenses in their eyes can no longer curve enough to bring nearby text into focus. Refraction also separates white light into its component colors because different wavelengths bend by different amounts. Blue light, with its shorter wavelength, bends more than red light, with its longer wavelength. When white light passes through a prism, this differential bending spreads the colors out into a spectrum, revealing the rainbow hidden within. This phenomenon is called dispersion, and it is responsible for the colored fringes you sometimes see at the edges of lenses, the fire in a diamond, and the most beloved optical phenomenon of all, the rainbow. A rainbow forms when sunlight enters a droplet of water, refracts as it crosses from air into water, reflects off the back of the droplet, and refracts again as it exits. Each of these interactions bends light, and the combination spreads the colors into an arc across the sky. The colors appear in a specific order: red on the outside, then orange, yellow, green, blue, and violet on the inside. This order is determined by how much each wavelength bends. Red bends the least and appears at the outer edge of the arc. Violet bends the most and appears at the inner edge. Every rainbow you see is unique to you. The light creating your rainbow comes from a specific set of raindrops located along a cone extending from the sun through your eyes to those drops. A person standing next to you sees a different rainbow, created by different drops at slightly different angles. You can never reach the end of a rainbow because the rainbow moves with you, always maintaining the same angular relationship between the sun, your eyes, and the rain. The full arc of a rainbow is actually a complete circle, but we usually see only the upper half because the ground gets in the way. From an airplane or a tall mountain, it is sometimes possible to see a rainbow's full circular form, a ring of color suspended in the air below. Double rainbows occur when light reflects twice inside each raindrop before exiting. The second reflection reverses the order of colors, so the outer, fainter rainbow has red on the inside and violet on the outside. The region between the two rainbows, called Alexander's dark band, appears darker than the surrounding sky because light is directed away from it by the geometry of the reflections. Occasionally, additional rainbows appear, called supernumerary arcs. These are faint bands of pastel colors inside the primary rainbow, caused by interference between light waves that have taken slightly different paths through the droplets. They are most visible when the raindrops are small and uniform in size. Fogbows are rainbows, formed by tiny droplets in fog rather than larger raindrops. Because the droplets are so small, diffraction smears the colors together, and the fogbow appears as a pale white arc, sometimes called a white rainbow or ghost rainbow. Fogbows are most often seen from ships at sea or in mountain valleys, where fog is common and the sun can shine through the mist. Moonbows, or lunar rainbows, are rainbows formed by moonlight instead of sunlight. Because moonlight is so much dimmer than sunlight, moonbows are faint and often appear white to the naked eye, though long exposure photographs reveal their colors. They are rare and magical, appearing only when the moon is bright, the sky is dark, and rain is falling in the right location. Beyond rainbows, the atmosphere produces a gallery of other optical phenomena, each one a gift of light and geometry. Halos are circles of light that appear around the sun or moon when high-altitude ice crystals refract sunlight. The most common halo has a radius of 22 degrees, created by light passing through hexagonal ice crystals in cirrus clouds. The crystals act as tiny prisms, bending light by the same angle regardless of their orientation, concentrating brightness into a ring. Sometimes the halo is joined by other features, bright spots called sundogs or parhelia, which appear on either side of the sun at the same height, arcs of light curving above and below, pillars of light extending vertically. These complex displays, called halo phenomena, can cover the entire sky with luminous geometry, a silent testament to the orderly architecture of ice. Sun pillars are vertical columns of light extending above or below the sun, most often seen at sunrise or sunset. They form when flat plate-like ice crystals float horizontally in the atmosphere, reflecting sunlight like millions of tiny mirrors. The pillar is not a beam, but a reflection, an image of the sun stretched vertically by the collective glint of countless crystals. Light pillars can also form over artificial light sources on cold nights. Street lights, parking lot lights, and city lights all can produce pillars when ice crystals fill the air. The result is a forest of vertical beams, each one marking a light source below, a strange and beautiful sight in the depths of winter. Coronas are small colored rings that appear immediately around the sun or moon, caused by diffraction of light by water droplets or ice crystals, unlike halos, which are large and formed by refraction. Coronas are small and formed by the bending of light around tiny particles. The size of the corona depends on the size of the droplets. Smaller droplets produce larger coronas. The corona is most easily seen around the moon on a slightly hazy night when thin clouds pass in front of it. The colors are soft and pastel, with blue on the inside and red on the outside, sometimes repeated in concentric rings. The effect is delicate, ephemeral, a quiet display of light-meeting atmosphere. Glories are colorful rings that appear around the shadow of your head when you look at mist or fog below you, with the sun behind you. They are most often seen from airplanes, appearing around the shadow of the aircraft on a layer of clouds below. The physics of glories is complex, involving a combination of diffraction, reflection, and something called surface waves that travel around the edges of droplets. Each person sees the glory centered on their own shadow, a personal halo that follows them through the sky. In ancient times, the phenomenon was called the specter of the Brocken, after a peak in Germany where climbers often saw their own enlarged shadows projected onto mist, surrounded by luminous rings. The green flash is one of the rarest and most fleeting optical phenomena. It occurs at the moment of sunrise or sunset, when a brief flash of green light appears at the upper edge of the sun. The flash lasts only a second or two, and many people spend years watching sunsets without ever seeing one. The green flash happens because of differential refraction. The atmosphere bends red light less than blue and green light. At sunset, as the sun sinks below the horizon, the red and orange parts of the sun disappear first. For a brief moment, only the more refracted green light remains visible. If the conditions are perfect, clear air, a sharp horizon, and stable atmospheric layering, the green becomes vivid enough to see. In rare cases, a blue flash may appear instead, or in addition to the green. This requires exceptionally clear air and usually occurs over the ocean, where there are no dust or pollutants to scatter the short wavelengths away. Photographs of the green flash reveal a brilliant emerald glow, startling in its intensity, a hidden feature of a phenomenon we see every day. Crepuscular rays are beams of sunlight that appear to radiate from a point in the sky, usually where the sun is located behind clouds or mountains. They are sometimes called God rays or Jacob's ladder, and they create dramatic, almost theatrical effects. As if the sky itself is being illuminated by a spotlight, the rays are actually parallel columns of light, made visible by dust, water droplets, or other particles in the air. They appear to diverge because of perspective, the same effect that makes railroad tracks seem to converge in the distance. The beams are all going the same direction, but they seem to spread out from a single source because of the geometry of vision. Anti-crepuscular rays are the same phenomenon seen from the opposite direction. They appear to converge on a point directly opposite the sun, meeting at the anti-solar point. These rays are often fainter and less commonly noticed, but they complete the geometry of the crepuscular display, showing that what appears to diverge in one direction must converge in another. The zodiacal light is a faint glow that extends along the plane of the solar system. visible after sunset or before sunrays in a truly dark sky. It is caused by sunlight scattering off countless dust particles that orbit the sun in the same plane as the planets. The light is so faint that it is invisible from cities and suburbs, but in dark locations, it can rival the brightness of the Milky Way. The Gegenschein, or counterglow, is an even fainter patch of light that appears directly opposite the sun in the night sky. It is caused by dust particles that are illuminated face on, reflecting sunlight directly back toward Earth. The Gegenschein is one of the faintest natural light sources visible to the naked eye, a whisper of light in the deep darkness of night. All of these phenomena are gifts of geometry and physics, patterns created by the interaction of light with matter and atmosphere. They require no special equipment to observe, only patience, attention, and the right conditions. They are reminders that the sky is not a featureless void, but a canvas of subtle shifting beauty. Reflection is the other great behavior of light, complementing refraction. When light strikes a surface and bounces back, we see the world. Without reflection, objects would be invisible, absorbing all light that touched them, revealing nothing of their shape or color. The law of reflection is simple. The angle at which light strikes a surface equals the angle at which it bounces away. A ray hitting a mirror at 30 degrees from perpendicular will reflect at 30 degrees on the other side. This perfect predictability is what allows mirrors to form images, bouncing light in orderly ways that preserve spatial relationships. Mirrors reverse left and right, or so it seems. Actually, mirrors do not reverse left and right at all. They reverse front and back. When you face a mirror, your image faces you, with its front pointing toward the mirror's surface and its back pointing away. Your left hand still appears on the left side of the image and your right hand on the right. The apparent reversal is a cognitive illusion, a confusion caused by imagining yourself rotated to face the direction the reflection faces. Flat mirrors produce images that appear to be behind the mirror, at the same distance as the object is in front. These are called virtual images, because the light does not actually come from behind the mirror. The rays bouncing off the mirror diverge as if they originated from a point behind the surface, and your brain interprets them accordingly. Curved mirrors behave differently. A concave mirror, curved like the inside of a spoon, can focus light to a point, producing real images that can be projected onto a screen. This is the principle behind reflecting telescopes, which use concave mirrors to gather and focus starlight. A convex mirror, curved like the back of a spoon, spreads light outward, producing virtual images that appear smaller and farther away than the object. The mirrors in car side view mirrors are slightly convex, which is why objects in them appear smaller than they are. The convex shape provides a wider field of view, allowing drivers to see more of the road behind them, at the cost of making distances harder to judge. Polished metal surfaces reflect almost all visible light, which is why they appear shiny. The electrons in metal are free to move, and they respond to incoming light waves by oscillating and re-emitting the light in the direction of reflection. Different metals have slightly different reflective properties, which is why silver mirrors look different from copper or gold. Glass reflects some light and transmits the rest. The amount reflected depends on the angle of incidence. When you look straight through a window, only about 4% of the light reflects back. But at grazing angles, when light strikes almost parallel to the surface, reflection increases dramatically. This is why windows become mirror-like when viewed from sharp angles. especially at night when the interior is brighter than the exterior. Water also reflects light, and the amount of reflection depends on the angle. At noon, when the sun is high, a lake may reflect only a small percentage of sunlight, allowing you to see into the depths. At sunset, when the sun is low, the water's surface becomes a mirror, reflecting the colors of the sky so perfectly that the boundary between water and air seems to vanish. Total internal reflection occurs when light traveling through a denser medium strikes the boundary with a less dense medium at a shallow angle. Instead of passing through, all the light bounces back. This is the principle that makes fiber optics work. Light enters a glass fiber and bounces along its length, trapped by total internal reflection, carrying signals across continents without escaping. Diamonds sparkle partly because of total internal reflection. The high refractive index of diamond means that light entering the gem bounces internally many times before finally escaping. A skilled diamond cutter arranges the facets to maximize these internal reflections, creating the flashes of brilliance and fire that make diamonds so prized. The sparkle of water, the glint of dew on a leaf, the shimmer of sunlight on waves, all of these are reflections, light bouncing from surface to surface, carrying information about shape and texture and motion. Every glitter and gleam is a message, a photon's report of where it has been and what it has touched. Shadows are the absence of light, the dark shapes that form when an object blocks photons from reaching a surface. They are negative images, outlines defined not by what is present, but by what is missing. And yet, shadows carry information, revealing the shape of the object that casts them, the direction of the light source, and the distance between object and surface. A shadow has two parts, the umbra and the penumbra. The umbra is the darkest central region, where all light from the source is blocked. The penumbra is the lighter outer region, where only some of the light is blocked. The relative size of these regions depends on the size of the light source and the distances involved. A point source of light infinitely small would cast shadows with no penumbra at all, sharp-edged silhouettes with no gradation. But real light sources have finite size, so their shadows always have some softness at the edges. The larger the source, the softer the shadow. The farther the object from the surface, the softer the shadow. The interplay of these factors creates the endless variety of shadows we see in the world. On a sunny day, the sun appears as a disk about half a degree across in the sky. This finite size means that outdoor shadows always have some softness, with the penumbra becoming more visible the farther the shadow is from the object. Shadows directly beneath an object are sharp. Shadows cast far across the ground are soft and diffuse. On a cloudy day, the entire sky becomes the light source, a vast dome of diffused illumination. Shadows nearly vanish because light comes from all directions and fills in the regions that would otherwise be dark. Photographers call this soft light, prized for portraits, because it minimizes harsh shadows and flatters skin. The shadows on the moon tell us something about the lunar surface. Because the moon has no atmosphere, there is no scattering to soften the edges. Shadows are pitch black and razor sharp, with no penumbra, no gradation. Astronauts found this disorienting, as the human eye is accustomed to using shadow softness as a depth cue. On the moon, every shadow looks like a bottomless void. Eclipses are the grandest shadows in the solar system. A solar eclipse occurs when the moon passes between the Earth and the Sun, casting its shadow on the Earth's surface. The umbra, the region of total shadow, is small, no more than a few hundred kilometers wide. Only those within the umbra see the sun completely blocked, the corona blazing around the moon's dark silhouette. The penumbra of a lunar shadow is much larger, covering thousands of kilometers. Those in the penumbra see a partial eclipse, with the moon blocking only part of the sun's disk. The deeper into the penumbra you are, the more of the sun is covered. A lunar eclipse occurs when the Earth passes between the sun and the moon, casting its shadow on the lunar surface. The moon does not disappear entirely during a lunar eclipse because Earth's atmosphere bends some sunlight into the shadow. The red and orange wavelengths bend the most, filtering through the atmosphere and painting the moon in shades of copper and rust. A totally eclipsed moon glows with the light of all the sunsets and sunrises on Earth, gathered and projected onto the lunar surface. The quality of light in shadows is not simply darkness. In outdoor settings, shadows receive skylight, the blue light scattered by the atmosphere. This is why shadows often have a bluish tint, particularly on snow, where the contrast between warm sunlit areas and cool shadowed areas is most visible. Painters have long known this, using complementary colors to render shadows more realistically. In the deep shadow of a forest, light filters through leaves, and the color of that light is green. The canopy absorbs red and blue for photosynthesis and transmits green, so the shadows beneath the trees are dappled with emerald light. Every environment has its own shadow color, shaped by the surfaces that reflect and filter the available light. Shadows move with the sun, tracing the passage of time across the ground. This observation gave rise to the sundial, one of the oldest timekeeping devices. A vertical stick, called a gnomon, casts a shadow that rotates as the sun crosses the sky. By marking the positions of the shadow at different hours, ancient peoples created clocks that needed no mechanism, only light and the steady motion of the earth. The length of shadows changes with the seasons. In summer, when the sun is high, shadows are short. In winter, when the sun is low, shadows stretch long across the ground. At noon, on the summer solstice at the Tropic of Cancer, the sun is directly overhead, and vertical objects cast no shadow at all. This observation helped ancient Greek scholars estimate the circumference of the Earth more than 2,000 years ago. Shadows can create optical illusions. The shadow of a crater on the moon can make it appear as a dome if the lighting is unfamiliar. Shadows cast by furrows in a field can make the ground seem to undulate. The brain uses shadows to infer three-dimensional shape, and when the lighting is unusual or ambiguous, those inferences can be wrong. In the quiet of night, when the sun has set and artificial lights are few, shadows merge into general darkness. The distinction between shadow and night becomes meaningless, because shadow is simply the absence of light, and night is shadow writ large, the shadow of the earth itself, cast into space by its own bulk. And now we turn to a different kind of light, one that does not come from the sun or stars or fire, but from living things themselves. Bioluminescence is the production of light by living organisms, a phenomenon found throughout the natural world, from the deepest oceans to the forests of summer nights. The most familiar bioluminescent creatures are fireflies, the beetles that flash in meadows and gardens on warm evenings. Their light is produced by a chemical reaction in specialized organs in their abdomens, an enzyme called luciferase catalyzes the oxidation of a molecule called luciferin, releasing energy in the form of light. The reaction is remarkably efficient, producing almost no heat, which is why firefly light is sometimes called cold light. Fireflies use their light to communicate. Each species has its own flash pattern, a code of blinks and pauses that allows males and females to find each other in the dark. Some species synchronize their flashes, thousands of individuals blinking in unison, creating waves of light that ripple through the forest. The mechanism by which they synchronize is not fully understood, but the result is one of the most beautiful displays in nature. In the oceans, bioluminescence is even more common. It is estimated that more than 3/4 of all sea creatures can produce light in some way. The darkness of the deep sea, where sunlight never reaches, is illuminated by countless living lights, a galaxy of glowing organisms drifting through the black water. Some fish have light organs called photophores, arranged in patterns along their bodies. These lights may serve to attract prey, to communicate with others of their kind, or to camouflage their silhouettes against the faint light filtering down from above. A fish viewed from below is visible as a dark shape against the brighter surface waters. But if it lights up its underside to match that brightness, it becomes invisible, hidden by its own glow. Anglerfish carry their light at the end of a fleshy stalk that dangles in front of their mouths. The light attracts prey, luring them close enough to be snapped up by the anglerfish's enormous jaws. The light itself is produced not by the fish, but by symbiotic bacteria that live in the lure, a partnership between species that benefits both. Many jellyfish are bioluminescent, their bodies pulsing with soft light as they drift through the sea. Some produce light when disturbed, a defensive display meant to startle predators or attract larger predators that might attack the attacker. Others glow continuously, their light a constant presence in the underwater dark. The vampire squid, despite its fearsome name, is a gentle creature that lives in the oxygen minimum zones of the deep ocean. Its entire body is covered with light-producing organs, and it can create complex patterns of light and dark that may confuse predators. When threatened, it can eject a cloud of bioluminescent mucus, a glowing decoy that distracts attackers while the squid escapes. Some species produce light that is not visible to human eyes. Certain deep-sea fish emit red light, which penetrates the darkness without alerting prey that cannot see red wavelengths. These fish have evolved special visual pigments that allow them to see their own red light, giving them a kind of biological night vision scope. On the surface of the ocean, bioluminescence often appears as a diffuse glow in the wake of boats or the breaking of waves. This light is produced by dinoflagellates, single-celled organisms that flash when disturbed. A swimmer moving through water rich in dinoflagellates leaves a trail of blue-green light, as if trailing stardust through the sea. On rare occasions, the concentration of bioluminescent organisms becomes so high that entire bays or coastlines glow at night. These events, sometimes called phosphorescent bays or bioluminescent bays, attract visitors from around the world who come to kayak or swim through water that lights up at every touch. Certain fungi also produce light. Bioluminescent mushrooms glow green in the darkness of tropical forests, their caps and stems emitting a soft luminescence that can be seen from meters away. The purpose of this light is still debated. It may attract insects that help disperse spores. It may be a byproduct of chemical processes with other functions. Whatever the reason, glowing mushrooms are among the most magical sights in nature. The chemistry of bioluminescence varies among organisms, but most involve some form of luciferin and luciferase. Different species have evolved these molecules independently, suggesting that the ability to produce light has arisen many times throughout evolutionary history. The advantage of making your own light in a world often shrouded in darkness is evidently significant enough to have evolved again and again. Bioluminescence has inspired human technology. Green fluorescent protein, originally isolated from jellyfish, is now used as a marker in molecular biology, allowing scientists to track genes and proteins inside living cells. Researchers have created glowing mice, glowing fish, and glowing plants by inserting the genes for bioluminescence into their genomes. One day, we may have trees that glow softly at night, providing illumination without electricity. We may have crops that signal when they need water by changing color or brightness. The possibilities are limited only by imagination and ethics, by our ability to understand and our willingness to apply what nature has already invented. As you lie here, perhaps with a small light on in your room, or perhaps in darkness, consider that you are surrounded by the potential for light. The atoms in your walls and ceiling and bedding are vibrating, emitting infrared radiation too faint for your eyes to see, but present nonetheless. If you could see in infrared, your room would glow with the warmth of objects at room temperature, a soft radiance emitted by everything around you. Your own body is a source of light. At the temperature of living tissue, you emit infrared radiation continuously, a gentle heat that dissipates into the air. Thermal cameras can see this light, rendering warm bodies as bright shapes against cooler backgrounds. In the infrared, you are luminous, a warm glow in the shape of a person. Even visible light emerges from the human body in tiny quantities. Researchers have detected ultra-weak bioluminescence from human skin, a glow about 1,000 times fainter than what the eye can perceive. The light is produced by chemical reactions involving free radicals and lipid oxidation in skin cells. It varies throughout the day, peaking in the late afternoon and subsiding at night. You are, quite literally, faintly glowing right now. This inner light is not visible to the naked eye and has no known biological function. It is simply a byproduct of the chemistry of life, a whisper of photons escaping from the metabolic reactions that keep you alive. In a sense, you're a bioluminescent organism, just one with a glow too faint to see. And so, in the quiet of this moment, you are both a receiver and an emitter of light. Photons from distant sources enter your eyes, carrying information about the world. Photons from your own body radiate outward, carrying information about your warmth. You are part of the great exchange of light that connects all things, a node in the luminous web that spans the universe. The history of life on Earth is a history of light. The first organisms to harvest light, the cyanobacteria that invented photosynthesis billions of years ago, transformed the planet. They filled the atmosphere with oxygen, changed the chemistry of the oceans, and made possible every form of life that followed. Without their ability to capture photons and convert them into chemical energy, life would have remained small and simple, confined to the margins of a hostile world. Eyes evolved to take advantage of light, to gather information about the environment without having to touch it. The first eyes were simple light-sensitive patches, able to distinguish light from dark but not to form images. Over hundreds of millions of years, these patches became more sophisticated, developing lenses, irises, and retinas, becoming the complex organs we possess today. The evolution of eyes changed the course of life. Predators could spot prey from a distance. Prey could see predators approaching. The visual arms race drove the development of camouflage, warning colors, and display patterns. The explosion of complex life in the Cambrian period, more than 500 million years ago, may have been triggered in part by the evolution of efficient eyes, which transformed the ecological landscape. Today, eyes come in astonishing variety. Insects have compound eyes made of thousands of tiny lenses, each capturing a small piece of the visual field. Scallops have dozens of eyes arranged along the edges of their shells, each with a mirror instead of a lens to focus light. The mantis shrimp has the most complex eyes known, capable of detecting polarization, ultraviolet, and a range of colors far beyond human vision. And yet, for all this diversity, every eye is doing the same thing: detecting light. Photons enter, stimulate receptors, and trigger neural signals that the brain interprets as vision. The specific mechanisms vary, but the fundamental principle is universal. Light is the medium through which life perceives the world. The light that enters your eyes right now has a history. Some of it may have been emitted moments ago by a lamp or a screen. Some may have been emitted 8 minutes ago by the sun, traveled through space, passed through the atmosphere, bounced off a surface, and finally reached you. If you are reading at night, the light may have been generated by electrons jumping between energy levels in an LED or a fluorescent tube, processes governed by quantum mechanics. Every photon that reaches you is a messenger, carrying information about where it has been and what it has encountered. The colors you see, the brightness you perceive, the shapes you recognize, all of these are stories told by light, decoded by your brain into the seamless experience of vision. And when you close your eyes, the light does not stop. It continues to fill the room, to bounce off the walls, to carry its messages to anyone or anything capable of receiving them. The universe is full of light, whether or not there are eyes to see it. The photons do not care if they are observed. They travel on, faithful to the laws of physics, indifferent to perception. In the darkness behind your eyelids, you may see faint patterns, swirls of color, points of light. These are not external photons, but internal signals, the spontaneous activity of your visual system, the noise of a neural network that never fully quiets. Even in complete darkness, your brain generates the illusion of light, so accustomed is it to the presence of photons. Perhaps as you rest, you will dream of light. Dreams often contain vivid visual imagery, created entirely by the brain without any input from the eyes. In dreams, you can see things that do not exist, visit places you have never been, witness events that never happened. The light of dreams is imaginary, yet it feels real, a testament to the brain's power to create experience from nothing but its own activity. And so, as this portion of our journey draws to a close, let the facts drift away like light through water, bending and softening as they go. You do not need to remember them. You do not need to hold on to anything. The light will still be there tomorrow, waiting for you, carrying its ancient messages through the dark. Rest now. Let your breath slow and your body relax. The universe is luminous, and you are part of its glow. Sleep and let the gentle light of dreams carry you through the night. Light is the foundation of almost all life on Earth. The energy that powers your body, that grew the food you ate today, that sustains the entire web of living things, all of it traces back to photons captured from the sun. Without light, the biosphere would collapse. The intricate dance of predator and prey, the forests and grasslands, the teeming oceans, all would fall silent without the steady stream of energy that arrives each day from our star. Photosynthesis is the process by which plants, algae, and certain bacteria capture light and convert it into chemical energy. It is one of the most important chemical reactions in the history of the planet, and it happens so quietly, so constantly, that we rarely pause to appreciate its magnificence. In every leaf, in every blade of grass, in every green cell floating in the ocean, tiny molecular machines are harvesting photons and using their energy to build the molecules of life. The key molecule in photosynthesis is chlorophyll, a pigment that absorbs red and blue light while reflecting green. This is why plants appear green to our eyes. The chlorophyll molecules are arranged in structures called photosystems, embedded in the membranes of chloroplasts, the organelles where photosynthesis takes place. When a photon of the right wavelength strikes a chlorophyll molecule, it excites an electron, boosting it to a higher energy level. That excited electron is the beginning of a cascade of reactions. It passes from molecule to molecule along an electron transport chain, releasing energy at each step. That energy is used to pump protons across a membrane, creating a gradient that drives the synthesis of ATP, the universal energy currency of cells. Meanwhile, the electrons are used to split water molecules, releasing oxygen as a byproduct and capturing hydrogen to build sugars. The oxygen you are breathing right now was released by photosynthesis. Every molecule of O2 in the atmosphere was once part of a water molecule inside a plant or bacterium, split apart by the energy of captured light. The air itself is a gift of photosynthesis, a byproduct of life's hunger for light. The sugars produced by photosynthesis are the foundation of nearly every food chain on Earth. Plants use them to build their own tissues, and animals eat the plants, and other animals eat those animals, and so on up the chain. Even the creatures of the deep sea, living far from sunlight, often depend on organic matter that drifts down from the sunlit surface, the remains of photosynthetic organisms that lived and died in the light. Some ecosystems operate independently of sunlight. Around hydrothermal vents on the ocean floor, bacteria use chemical energy from volcanic gases to build organic molecules, a process called chemosynthesis. These bacteria form the base of food webs that include tubeworms, clams, shrimp, and fish, all thriving in total darkness. But these ecosystems are exceptions. The vast majority of life on Earth is powered, directly or indirectly, by light. The efficiency of photosynthesis is remarkable, but not perfect. Plants typically convert only about 1 to 2% of the sunlight that strikes their leaves into chemical energy. The rest is reflected, transmitted, or lost as heat. Even so, the total amount of energy captured by photosynthesis is staggering. Each year, photosynthetic organisms fix more than 100 billion tons of carbon, storing energy equivalent to several times humanity's total energy consumption. Scientists have long dreamed of artificial photosynthesis, systems that could capture sunlight and convert it directly into fuel with greater efficiency than plants achieve. Progress has been made, but the complexity of natural photosynthesis, honed by billions of years of evolution, remains difficult to replicate. The molecular machinery inside a chloroplast is a nanotechnology of extraordinary sophistication, and we are still learning how it works. Light also regulates the lives of organisms in ways that go beyond energy capture. The cycles of day and night, the changing lengths of days through the seasons, the angle of sunlight, all of these carry information that living things use to coordinate their activities with the rhythms of the planet. Circadian rhythms are internal clocks that run on a roughly 24-hour cycle, governing sleep, wakefulness, hormone release, body temperature, and countless other physiological processes. Almost every organism on Earth has some form of circadian rhythm, from bacteria to humans. These rhythms are not simply responses to external light. They are built into the very fabric of cellular biology, running even in the absence of environmental cues. But light is the primary signal that synchronizes circadian rhythms with the external world. In humans, specialized cells in the retina called intrinsically photosensitive retinal ganglion cells detect light levels and send signals to the suprachiasmatic nucleus, a tiny region in the hypothalamus that serves as the body's master clock. When light enters the eyes in the morning, it resets the clock, signaling that a new day has begun. This is why exposure to bright light in the morning helps you feel awake and alert, and why exposure to light at night can disrupt sleep. The blue wavelengths of light are particularly effective at suppressing melatonin, the hormone that promotes sleepiness. Screens that emit blue-rich light can delay the onset of sleep if used too close to bedtime, a modern problem that our ancestors never faced. Before electric lighting, humans lived in synchrony with the sun. They rose at dawn, worked through the day, and retired to darkness when the sun set. Firelight and candles provided some illumination, but their dim, warm glow did not significantly disrupt circadian rhythms. The invention of artificial lighting extended the day, but it also disconnected us from the natural cycles that had governed human life for hundreds of thousands of years. Seasonal changes in day length also affect biology. Many animals use the changing length of days to time their reproduction, migration, and hibernation. As days grow shorter in autumn, birds prepare to migrate south. As days grow longer in spring, mammals come out of hibernation and begin to breed. These responses are mediated by hormones that are themselves regulated by light exposure. In humans, seasonal changes in light can affect mood and energy levels. Seasonal affective disorder, sometimes called winter depression, is a condition in which people experience low mood, fatigue, and other symptoms during the darker months of the year. Light therapy, exposure to bright artificial light in the morning, can help reset circadian rhythms and alleviate symptoms. The treatment works because it mimics the effects of natural sunlight, telling the brain that longer days have arrived. Plants also respond to day length, a phenomenon called photoperiodism. Some plants flower only when days are long, such as spinach and lettuce. Others flower only when days are short, such as chrysanthemums and poinsettias. Still others are day neutral, flowering regardless of day length. Farmers and gardeners use this knowledge to manipulate flowering times, extending or shortening the growing season with artificial light or shade. The color of light affects plant growth as well. Blue light promotes compact, bushy growth, while red light encourages elongation and flowering. Plants grown under only green light, the wavelengths they reflect rather than absorb, grow poorly, starved for the colors they need. Indoor growers use carefully tuned LED lights to provide optimal spectra for different crops at different stages of development. Light shapes the structure of ecosystems. In forests, the canopy captures most of the sunlight, leaving the understory in dim shade. Plants that live on the forest floor have evolved to thrive in low light, with large leaves and efficient photosynthetic machinery. Gaps in the canopy created by fallen trees allow shafts of sunlight to reach the ground, triggering bursts of growth as understory plants race to capture the temporary abundance. In the ocean, light penetrates only the upper layers. The sunlit zone, or euphotic zone, extends to about 200 meters in clear water, less in murky coastal areas. Below this, in the twilight zone and the midnight zone, photosynthesis is impossible, and life depends on organic matter sinking from above or on chemosynthesis at hydrothermal vents. The distribution of life in the ocean is fundamentally determined by the availability of light. Coral reefs exist only in shallow, clear water because the symbiotic algae that live inside coral tissues need light for photosynthesis. These algae provide most of the coral's energy, and in return, the coral provides shelter and nutrients. When water temperatures rise or conditions change, the algae may be expelled, leaving the coral bleached and starving. Coral bleaching is one of the most visible consequences of climate change, a reminder of how dependent these ecosystems are on stable conditions for light and temperature. Migration patterns are often timed by light. Many birds migrate at night, navigating by the stars in the Earth's magnetic field. They begin their journeys when the days reach a certain length, responding to photoperiod rather than temperature or food availability. This ensures that they arrive at their breeding or wintering grounds at the optimal time, even in years when weather patterns are unusual. Sea turtles hatch at night and crawl toward the brightest horizon, which, in natural conditions, is the ocean reflecting starlight and moonlight. Artificial lights on beaches can disorient hatchlings, drawing them inland instead of toward the sea. Conservation efforts often include managing lighting near nesting beaches to give hatchlings a chance to find the water. Even single-celled organisms respond to light. Many bacteria and algae have light-sensitive proteins that allow them to swim toward or away from illumination, positioning themselves for optimal photosynthesis or avoiding damaging ultraviolet rays. These simple responses are the evolutionary ancestors of more complex visual systems, the first steps on the path that led to eyes. The relationship between light and life is ancient and intimate. For billions of years, organisms have been bathed in sunlight, and they have evolved countless ways to use it, avoid it, sense it, and respond to it. Light is not just a source of energy. It is an information signal, a timekeeper, a navigator, a regulator of growth and behavior. Life on Earth is shaped by light as surely as it is shaped by water or air. And now, let us turn our gaze upward to the light that comes from beyond our world. Starlight, the ancient photons that have traveled across the void to reach us, carrying messages from distant suns. When you look at the night sky, you're looking back in time. The light from each star left its source years, decades, centuries, or millennia ago, and only now is it arriving at your eyes. The farther away a star, the older its light. When you see the North Star, Polaris, you are seeing it as it was about 430 years ago, around the time Shakespeare was writing his plays. The light left Polaris during the Renaissance and has been traveling ever since. The nearest star to the Sun is Proxima Centauri, a small red dwarf about 4.2 light-years away. Its light takes a little over 4 years to reach us. If Proxima Centauri were to suddenly vanish, we would not know for more than 4 years. We would continue to see it shining in the sky, a ghost image of a star that no longer existed. Sirius, the brightest star in the night sky, is about 8.6 light-years away. Its light has been traveling for nearly 9 years by the time it enters your eyes. Sirius is actually a binary system, 2 stars orbiting each other, but the companion is too faint to see without a telescope. Betelgeuse, the red supergiant that marks the shoulder of Orion, is roughly 600 to 700 light-years distant. The light you see from Betelgeuse tonight left the star during the Middle Ages. Betelgeuse is nearing the end of its life and will one day explode as a supernova. When it does, it will become bright enough to see during the day. But we will not see the explosion until its light reaches us, centuries after the event occurs. The Pleiades, the cluster of stars also known as the Seven Sisters, is about 440 light-years away. The light arriving from the Pleiades tonight began its journey around the time Galileo was turning his telescope toward the sky. The stars themselves are young by cosmic standards, only about 100 million years old, born from the same cloud of gas and still moving together through space. The Andromeda Galaxy is the most distant object visible to the naked eye, a faint smudge of light about 2.5 million light-years away. The photons entering your eyes from Andromeda have been traveling since before the genus Homo existed on Earth. They left Andromeda when our ancestors were still small-brained apes on the African savanna. Looking at Andromeda is looking into a past so deep it predates humanity itself. With telescopes, we can see much farther. The Hubble Space Telescope and its successors have captured light from galaxies more than 13 billion light-years away. These galaxies are seen as they were when the universe was less than 1 billion years old, young and turbulent and very different from the cosmos we know today. The light from these distant galaxies has been traveling for almost the entire history of the universe. The most distant light we can detect is not from any star or galaxy. It is the cosmic microwave background, the afterglow of the Big Bang itself. This light was released about 380,000 years after the universe began, when the hot plasma that filled all of space cooled enough for neutral atoms to form. Before that moment, the universe was opaque, filled with a fog of charged particles that scattered light in every direction. After that moment, light could travel freely, and it has been doing so ever since. The cosmic microwave background fills the entire sky. It comes from every direction uniformly, with only tiny variations in temperature. Those variations, measured to exquisite precision by satellites like COBE, WMA, and Planck, reveal the seeds of all the structure we see in the universe today. Slightly denser regions in the early universe pulled in more matter over billions of years, becoming galaxies and galaxy clusters. Slightly less dense regions became the voids between them. When the cosmic microwave background was first released, it was visible light, the glow of a universe at a temperature of about 3,000 degrees. But as the universe expanded, space itself stretched, and the wavelengths of that light stretched with it. What was once visible, light has been redshifted into microwaves, radiation with wavelengths measured in millimeters. The glow is still there, filling all of space, but our eyes cannot see it. We need radio telescopes to detect it. The discovery of the cosmic microwave background in 1965 was one of the most important confirmations of the Big Bang theory. Arno Penzias and Robert Wilson, working at Bell Labs, detected a persistent noise in their radio antenna that they could not explain. After ruling out every possible source of interference, including pigeon droppings in the antenna, they realized they were detecting the remnant heat of the early universe. They won the Nobel Prize for their discovery. The cosmic microwave background is the oldest light in the universe. It has been traveling for more than 13 billion years, crossing the expanding void, carrying information about the conditions just a few 100,000 years after the beginning of everything. When we study this light, we are studying the infancy of the cosmos, reading the earliest messages the universe has to offer. Beyond the cosmic microwave background, there is a wall of darkness. We cannot see anything from before 380,000 years after the Big Bang, because before that time, the universe was opaque. The light from that earlier era was absorbed and re-emitted countless times, losing any information it might have carried. The cosmic microwave background marks the boundary of the observable past, the edge of what we can see. But we may one day detect echoes from even earlier times. Gravitational waves, ripples in the fabric of space-time, could carry information about the first moments of the universe, when space was expanding faster than light and the fundamental forces were still unified. Experiments are underway to detect these primordial waves, though they are extraordinarily faint and difficult to distinguish from other signals. The light from stars is not just old, it is also informative. By analyzing the spectrum of starlight, astronomers can determine what elements are present in a star, how hot it is, how fast it is moving, and even whether it has planets. Each element absorbs and emits light at specific wavelengths, creating a unique fingerprint of dark or bright lines in the spectrum. This technique, called spectroscopy, has revealed the composition of stars across the universe. We know that stars are made mostly of hydrogen and helium because their spectra show the characteristic lines of those elements. We know that heavier elements, forged in the cores of massive stars and scattered by supernova explosions, are present in younger stars because their spectra show lines of iron, calcium, oxygen, and carbon. The chemical history of the galaxy is written in starlight. The Doppler effect allows astronomers to measure the motion of stars. When a star moves toward us, its light is shifted slightly toward the blue end of the spectrum. When it moves away, the shift is toward the red. By measuring these shifts, we can determine how fast stars are moving and in what direction. This technique has revealed the rotation of galaxies, the expansion of the universe, and the presence of planets orbiting distant stars. When a planet passes in front of its star, it blocks a tiny fraction of the star's light, causing a slight dimming that can be detected by sensitive instruments. This is the transit method, one of the most successful techniques for discovering exoplanets. By measuring how much the light dims and for how long, astronomers can determine the size of the planet and its orbital period. Follow-up observations can reveal the planet's atmosphere by analyzing how starlight filters through it. The James Webb Space Telescope, launched in 2021, is designed to study the infrared light from the most distant galaxies and the atmospheres of exoplanets. Its mirror, more than 6 meters across, gathers light that has been traveling for billions of years, focusing it onto instruments of unprecedented sensitivity. Webb is already revealing details of the early universe that were invisible to previous telescopes, pushing back the frontier of observable time. Light carries not just information, but also momentum. When photons strike a surface, they exert a tiny pressure, pushing against the material they hit. This radiation pressure is imperceptible in everyday life, but it has real effects on cosmic scales. The tails of comets point away from the sun because solar radiation and the solar wind push dust and gas outward. The balance between gravity and radiation pressure determines the size of stars, preventing them from collapsing under their own weight. Solar sails exploit radiation pressure for propulsion. By unfurling a large reflective surface, a spacecraft can be pushed by sunlight, accelerating gradually over time. The acceleration is small, but it is continuous and requires no fuel. Over months and years, a solar sail can reach speeds far beyond what chemical rockets could achieve for long-duration missions. In the cores of the most massive stars, radiation pressure is so intense that it can tear the star apart. These stars, called hypergiants, are on the edge of stability, their enormous luminosity threatening to blow their outer layers into space. Some hypergiants are surrounded by shells of gas they have ejected, still glowing with the light of their central star. The interplay of light and matter shapes the universe at every scale. Light heats planets and moons, driving weather and climate. Light triggers chemical reactions in atmospheres, creating smog on Earth and haze on Titan. Light illuminates the dust between stars, revealing the structure of nebulae. Light from the Big Bang still bathes every corner of the cosmos, a faint but universal presence. And now we arrive at one of the deepest mysteries of light, a mystery that has puzzled physicists for more than a century and remains at the heart of our understanding of reality: the quantum nature of light. In the early 20th century, physicists discovered that light does not behave the way classical physics predicted. Experiments revealed that light comes in discrete packets of energy, called quanta or photons. The energy of each photon is determined by its frequency. High-frequency light, like ultraviolet or X-rays, consists of high-energy photons. Low-frequency light, like radio waves, consists of low-energy photons. This discovery arose from attempts to explain a phenomenon called black-body radiation. When an object is heated, it glows, emitting light across a range of wavelengths. Classical physics predicted that the intensity of this radiation should increase without limit at short wavelengths, a result called the ultraviolet catastrophe. But experiments showed that the intensity actually peaked at a certain wavelength and then declined. The only way to explain this was to assume that energy was emitted in discrete amounts, not continuously. Max Planck introduced the idea of energy quanta in 1900, and Albert Einstein extended it in 1905, proposing that light itself was quantized. Einstein's explanation of the photoelectric effect, the emission of electrons from metal surfaces struck by light, earned him the Nobel Prize and established the photon as a fundamental particle. Light was not just a wave. It was also a stream of particles. But light had been known to behave like a wave for centuries. Interference and diffraction, phenomena that only waves can produce, had been demonstrated and explained. How could light be both a wave and a particle? The answer, according to quantum mechanics, is that it is neither or both, depending on how you look at it. The wave-particle duality of light is not a contradiction. but a feature of nature at the quantum scale. When light propagates through space, it spreads out like a wave, interfering with itself and diffracting around obstacles. But when light is absorbed or emitted, it does so in discrete quanta, individual photons with specific energies. The wave describes the probability of where a photon might be found. The particle is what is actually detected. The famous double-slit experiment demonstrates this duality in its starkest form. When light passes through two narrow slits, it creates an interference pattern on a screen behind them. Bands of brightness and darkness caused by waves overlapping constructively and destructively. This is exactly what you would expect from a wave. But if you reduce the intensity of the light until only one photon passes through at a time, something remarkable happens. Each photon lands on the screen at a specific point, like a particle, but over time, as many photons accumulate, the interference pattern emerges. Each individual photon somehow interferes with itself, as if it passed through both slits at once and interacted with its own waviness. If you try to detect which slit the photon went through, the interference pattern disappears. The act of observation changes the outcome. The photon behaves like a particle when observed, passing through one slit or the other, and the pattern on the screen becomes two bright bands, not an interference pattern. This is not a limitation of our instruments. It is a fundamental feature of quantum mechanics. Observation affects reality. This leads to the concept of superposition. Before a measurement is made, a quantum system exists in a combination of all possible states. The photon passing through the double slit is in a superposition of going through the left slit and going through the right slit. Only when a measurement is made does the superposition collapse into a single, definite state. The act of measurement forces reality to choose. Quantum mechanics is strange, but it works. It predicts the behavior of light and matter with extraordinary precision. Every technology that relies on quantum effects, from lasers to semiconductors to MRI machines, confirms its accuracy. The weirdness is not a flaw, but a feature of the universe at small scales. Entanglement is another quantum phenomenon involving light. Two photons can be created in such a way that their properties are correlated, no matter how far apart they are. If you measure the polarization of one photon, you instantly know the polarization of the other, even if it is on the opposite side of the galaxy. This correlation is stronger than any classical explanation can account for, a feature that Einstein called spooky action at a distance. Entanglement does not allow faster-than-light communication. You cannot use it to send messages instantaneously because the results of measurements appear random until compared with the results from the other photon. But it does reveal that quantum systems can be connected in ways that defy our intuitions about locality and separateness. The universe at the quantum level is more interconnected than it appears. These discoveries have practical applications. Quantum cryptography uses the properties of photons to create communication channels that are theoretically unbreakable. Any attempt to eavesdrop on a quantum encrypted message disturbs the photons in detectable ways, alerting the communicators to the intrusion. Quantum computers, still in their infancy, use superposition and entanglement to perform calculations that would be impossible for classical machines. The quantum nature of light is not something we experience directly. Our eyes and brains evolved to deal with the macroscopic world, where quantum effects average out and classical physics provides a good approximation. But the quantum world underlies everything. The stability of atoms, the chemistry of molecules, the behavior of materials, all depend on quantum mechanics. Light is our window into that deeper reality. Lasers are a technology that exploits the quantum properties of light. In a laser, atoms or molecules are excited to higher energy levels and then stimulated to emit photons in a coordinated way. The result is light that is coherent, meaning all the photons have the same wavelength, the same phase, and travel in the same direction. This coherence gives laser light its unique properties, its ability to be focused to a tiny point, to travel long distances without spreading, to carry information with precision. The word laser stands for light amplification by stimulated emission of radiation. The process begins with pumping energy into a medium, such as a gas, crystal, or semiconductor, to excite the atoms. When a photon of the right wavelength passes by an excited atom, it can stimulate the atom to emit an identical photon, in phase with the original. These two photons can stimulate more emissions, creating a cascade of coherent light. Mirrors at the ends of the laser cavity bounce the light back and forth, amplifying it with each pass, until it is intense enough to escape through a partially transparent mirror. Lasers have countless applications. They read and write data on optical discs. They carry signals through fiber optic cables. They cut and weld materials in manufacturing. They perform delicate surgeries on eyes and other tissues. They measure distances with extraordinary accuracy, from the tiny gaps in computer chips to the vast distances between Earth and reflectors left on the Moon by Apollo astronauts. Laser cooling uses light to slow atoms to near absolute zero. By tuning a laser to a frequency slightly below the resonance of an atom, scientists can arrange for atoms moving toward the laser to absorb photons and recoil, losing momentum. Atoms moving away are less likely to absorb because the Doppler shift moves them out of resonance. The net effect is that atoms are slowed from all directions, cooling the sample to temperatures of microkelvin or below. At these extreme temperatures, atoms behave in ways that are impossible to observe at higher temperatures. They can form Bose-Einstein condensates, states of matter in which thousands of atoms occupy the same quantum state and act as a single entity. They can be trapped in optical lattices, grids of light that hold atoms in place for study. The precision of atomic clocks, the most accurate timekeepers ever built, depends on laser-cooled atoms. Light is also used to trap and manipulate tiny objects. Optical tweezers use focused laser beams to grip particles ranging from bacteria to beads of glass. The gradient of the light intensity creates a force that pulls particles toward the focus, holding them in place. By moving the beam, researchers can move the particle, rotating it, stretching it, or bringing it into contact with other particles. Optical tweezers have revolutionized the study of biological molecules, allowing scientists to measure the forces exerted by single proteins and the mechanics of DNA. The quantum nature of light also explains why the night sky is dark. This might seem like a trivial observation, but it puzzled astronomers for centuries. If the universe is infinite and filled with stars, then every line of sight should eventually end at a star, and the sky should be as bright as the surface of a star in every direction. This paradox, known as Olber's paradox, has several resolutions, all related to the nature of light and the universe. First, the universe is not infinitely old. Light from very distant stars has not yet had time to reach us. The observable universe has a finite age, about 13.8 billion years, and we can only see objects whose light has had time to arrive. Second, the universe is expanding. Light from distant galaxies is redshifted, stretched to longer wavelengths as space expands. The most distant light has been redshifted out of the visible spectrum entirely into infrared and microwave wavelengths. Third, stars have finite lifetimes. They are not eternal beacons, but temporary flares that burned for millions or billions of years before fading. The combination of these factors ensures that the night sky is dark, punctuated only by the light of nearby stars and galaxies. The darkness of the night sky is itself a kind of light, a faint glow of ancient photons from the cosmic microwave background, and the integrated light of all the galaxies too faint to see individually. Even in the darkest places on Earth, far from any artificial light, the sky is not perfectly black. It glows with the remnants of creation, a whisper of light that fills all of space. And so, as we rest here together, surrounded by whatever light illuminates this moment, we are connected to the entire history of the universe. The photons striking your eyes have traveled from lamps or screens, from the sun or the stars, from the very beginning of time. They carry energy and information, warmth and beauty. They ask nothing of you. They simply arrive, faithful messengers from across the cosmos. The light around you will continue long after you fall asleep. It will bounce off the walls, pass through windows, radiate from warm surfaces, fill the room with its invisible presence. Even in complete darkness, photons are there, too faint for your eyes to detect, but present nonetheless. The universe never stops glowing. Let your eyes grow heavy. Let the strangeness of quantum mechanics and the vastness of cosmic distances drift away like light through a prism, separating into colors and then fading into the soft darkness behind your eyelids. You do not need to understand any of this. You do not need to remember it. The light will still be there tomorrow and the night after, and for billions of years to come. Rest now. The universe is luminous, and you are part of its glow. The same atoms that form your body were forged in ancient stars, and the light from those stars is still traveling through space, still carrying the signatures of their birth. You are made of star stuff, warmed by starlight, resting in a universe that has been shining since the beginning of time. Sleep well, and let the gentle light of dreams carry you through the night. For as long as humans have existed, we have gathered around light. The campfire was the center of early human life, a source of warmth, protection, and community. Around the fire, our ancestors cooked food, warded off predators, and shared stories that became the first threads of culture. The flickering flames held back the darkness of the night, creating a circle of safety in a dangerous world. Fire was humanity's first technology for controlling light. Unlike the sun, which rose and set according to its own schedule, fire could be kindled at will, extending the day into the night. This simple innovation transformed human society. It allowed our ancestors to inhabit caves and shelters that would otherwise have been too dark. It enabled them to venture into colder climates, where warmth was essential for survival. It created spaces for social bonding that strengthened the ties between individuals and groups. The oldest evidence of controlled fire dates back at least 1 million years to sites in Africa and the Middle East, where ancient hominins left behind burned bones and charred plant remains. By the time modern humans emerged, Fire was a universal technology, mastered by every human culture on every inhabited continent. The ability to make and control fire is one of the defining characteristics of our species. The light of fire is warm and orange, rich in the long wavelengths that our eyes perceive as comforting. This is no coincidence. We evolved in the presence of firelight, and our visual systems and emotional responses are tuned to its spectrum. The warm glow of candles and incandescent bulbs feels cozy and relaxing because it resembles the light that surrounded our ancestors for hundreds of thousands of years. Torches were among the earliest portable light sources. Bundles of wood or reeds soaked in animal fat or resin. They allowed humans to explore caves, travel at night, and carry light from place to place. Cave paintings deep underground, far from any natural light, were created by the flickering illumination of torches and oil lamps. The artists who made these images worked in conditions we can barely imagine, painting by the dim light of burning fat in the silent darkness of the earth. Oil lamps appeared thousands of years ago, burning animal fats, plant oils, or petroleum seeps in shallow vessels with wicks. They provided steadier, longer-lasting light than torches, and they could be left burning unattended. Lamps became fixtures of homes, temples, and public spaces, their flames dancing through the night. Candles emerged later, made from tallow, beeswax, or other solid fats molded around a wick. They were portable, relatively clean, and easy to store. For centuries, candles were the primary source of artificial light in much of the world. The wealthy burned beeswax candles, which were expensive but produced a clear, pleasant light. The poor made do with tallow candles, which were cheaper but smoked and smelled of rendered fat. The development of whale oil in the 18th and 19th centuries brought brighter, cleaner-burning lamps to those who could afford them. Whale oil was prized for its luminosity and lack of odor, and the whaling industry grew to meet the demand. Entire fleets sailed the world's oceans, hunting whales to light the homes and streets of growing cities. Kerosene, derived from petroleum, replaced whale oil in the mid-19th century. It was cheaper, more abundant, and burned brightly in specially designed lamps. The kerosene lamp became a fixture of rural life, providing light to farms and villages, far from the gas lines that illuminated cities. In many parts of the world, kerosene lamps remained the primary source of artificial light well into the 20th century. Gaslighting arrived in the early 19th century, first in factories and streets, then in homes. Coal gas, produced by heating coal in the absence of air, was piped through networks of underground pipes to burners that produced a bright, steady flame. Gaslighting transformed cities, making streets safer and enabling nightlife to flourish. Theaters, restaurants, and shops could stay open after dark, and the rhythm of urban life shifted accordingly. The gas lamp era was brief, but transformative. For the first time, artificial light was abundant and reliable enough to change the structure of society. Working hours extended into the evening. Social gatherings moved indoors. The night, once a time of rest and danger, became a time of activity and commerce. And then came electricity. The incandescent light bulb, developed independently by Thomas Edison and Joseph Swan in the late 1870s, changed everything. By passing electric current through a thin filament, the bulb produced light without flame, without smoke, without the need for constant refueling. It was clean, safe, and could be switched on and off instantly. Edison did not just invent the light bulb. he created an entire system for generating, distributing, and using electricity. His Pearl Street station in New York City, which opened in 1882, was the first central power plant supplying electricity to customers in the surrounding neighborhood. Within a few decades, electric lighting had spread across the industrialized world, displacing gas and kerosene almost entirely. The filament in an incandescent bulb glows because it is heated to a high temperature, typically around 2,700 degrees Celsius. At this temperature, the filament emits light across a broad spectrum, peaking in the infrared but extending into the visible range. Only a small fraction of the energy used by an incandescent bulb becomes visible light. The rest is radiated as heat, which is why incandescent bulbs are warm to the touch. Despite their inefficiency, incandescent bulbs dominated lighting for more than a century. Their warm color temperature and smooth, continuous spectrum made them pleasing to the eye. They were simple, inexpensive, and familiar. Generations grew up under their glow, and the warm light of an incandescent bulb became synonymous with home and comfort. Fluorescent lighting emerged in the mid-20th century, offering much greater efficiency than incandescent bulbs. A fluorescent tube contains a gas, usually mercury vapor, that emits ultraviolet light when excited by an electric current. The inside of the tube is coated with a phosphor that absorbs the ultraviolet and re-emits it as visible light. Fluorescent lights use about a quarter of the energy of incandescent bulbs to produce the same amount of light. But fluorescent light has a different quality. It tends to be cooler in color, with a spectrum that peaks at certain wavelengths determined by the phosphor coating. Early fluorescent lights had a harsh greenish cast that many people found unpleasant. Improvements in phosphor technology have produced warmer, more natural-looking fluorescent lights, but the perception of coldness persists. Compact fluorescent lamps, or CFLs, brought fluorescent efficiency to standard light fixtures. They could be screwed into ordinary sockets, replacing incandescent bulbs directly. Governments around the world encouraged or mandated the switch to CFLs as a way to reduce energy consumption and greenhouse gas emissions. But CFLs had drawbacks. They contained small amounts of mercury, requiring special disposal. They took time to reach full brightness, and many people simply preferred the light of incandescent bulbs. Light-emitting diodes, or LEDs, represent the latest revolution in lighting. An LED produces light through a process called electroluminescence, in which electrons passing through a semiconductor release energy as photons. LEDs are extraordinarily efficient, converting a much higher fraction of electrical energy into light than any previous technology. They last for tens of thousands of hours, far longer than incandescent or fluorescent bulbs. And they can be tuned to produce almost any color or color temperature. The blue LED, invented in the 1990s, was the breakthrough that made white LEDs possible. By combining a blue LED with a phosphor coating that converts some of the blue light into yellow, manufacturers can produce light that appears white to the eye. The inventors of the blue LED, Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura, received the Nobel Prize in Physics in 2014 for their work. Today, LEDs are rapidly replacing all other forms of lighting. They illuminate homes, offices, streets, and stadiums. They glow in screens of all sizes, from smartphones to billboards. They are found in car headlights, traffic signals, and decorative displays. The LED revolution is transforming the way we light the world, reducing energy consumption and enabling new applications that were impossible with previous technologies. Smart lighting systems can now adjust color temperature and brightness throughout the day, mimicking the natural progression of sunlight. Warm, dim light in the evening can help prepare the body for sleep. Bright, blue-rich light in the morning can help wake you up and reset your circadian rhythm. These systems recognize that light is not just illumination, but also a biological signal, and they attempt to align artificial lighting with the needs of the human body. The transformation brought by artificial light is difficult to overstate. Before electric lighting, the night was dark. People rose with the sun and retired when it set. Activities after dark were limited by the cost and inconvenience of candles and oil lamps. The night was a time of rest, of vulnerability, of ghosts and fears. Electric light banished the darkness. Factories could operate around the clock. Cities never slept. Entertainment and commerce continued long after sunset. The boundary between day and night blurred, and the rhythms of human life shifted to accommodate the new abundance of light. This transformation brought many benefits. Productivity increased. Safety improved. Education and literacy spread as people could read after dark without straining their eyes by candlelight. Medicine advanced as surgeons could operate under bright, steady illumination. The quality of life improved in countless ways. But the abundance of artificial light also brought costs. The most visible is light pollution, the brightening of the night sky by artificial sources. In cities and suburbs, the sky is never truly dark. The stars are washed out by the glow of streetlights, buildings, and signs. The Milky Way, once visible to every human who looked up at night, has become invisible to a third of the world's population. Light pollution is not just an aesthetic problem. It affects ecosystems in profound ways. Many animals rely on darkness for feeding, mating, and migration. Sea turtle hatchlings, drawn toward the brightest horizon, are disoriented by beachfront lighting and may never reach the ocean. Migrating birds are attracted to illuminated buildings, where they collide with glass and die by the millions each year. Insects swarm around artificial lights, exhausting themselves and disrupting pollination. The circadian rhythms of animals, including humans, are disrupted by artificial light at night. Exposure to light after sunset suppresses melatonin production and delays sleep. Chronic sleep disruption is associated with a range of health problems, from obesity and diabetes to cardiovascular disease and depression. The very technology that extended our days may be undermining our health. Efforts are underway to reduce light pollution and mitigate its effects. Dark sky preserves have been established in remote areas where artificial lighting is minimized to preserve the natural night. Shielded fixtures direct light downward where it is needed rather than upward into the sky. Warm-colored lights, which scatter less in the atmosphere, are replacing the blue-white lights that contribute most to sky glow. Astronomers have been among the most vocal advocates for dark skies. Light pollution makes it increasingly difficult to observe faint objects from ground-based observatories. Some of the best remaining dark sites are in remote deserts, on mountaintops, and on islands far from population centers. The construction of new observatories must take light pollution into account, seeking locations where the sky is still dark enough for serious research. For most of human history, the night sky was a source of wonder and navigation. The stars guided travelers across deserts and oceans. The phases of the moon marked the passage of time, the patterns of the constellations were woven into myth and religion. To lose the night sky is to lose a connection to our past, to the universe, and to our sense of place in the cosmos. And yet, even as we dim the stars with our lights, we continue to seek them. Satellites and space telescopes observe the universe from above the atmosphere, free from the interference of earthly light. Amateur astronomers travel to dark sites with portable telescopes, chasing the deepest views of the cosmos. The hunger to see the stars, to understand our place among them, persists despite all the obstacles we have created. Light has always been a symbol in human culture, carrying meanings that transcend its physical properties. In nearly every tradition, light represents knowledge, goodness, and hope. Darkness represents ignorance, evil, and fear. We speak of enlightenment, of seeing the light, of the light at the end of the tunnel. These metaphors are so deeply embedded in language that we hardly notice them. Religious traditions around the world celebrate light. Diwali, the Hindu festival of lights, marks the victory of good over evil and knowledge over ignorance. Hanukkah commemorates the miracle of a single day's oil burning for 8 nights. Christmas falls near the winter solstice, when the days begin to lengthen and light returns to the world. The solstice itself has been celebrated by countless cultures as a turning point, a promise that the sun will come back. The symbolism of light is not arbitrary. It reflects the biological and psychological importance of light to human survival. We are diurnal creatures, active during the day and vulnerable at night. Our ancestors depended on sunlight for warmth, for finding food, for seeing threats. The emotional associations we have with light are grounded in millions of years of evolutionary history. Artists have always been fascinated by light. The painters of the Renaissance developed techniques for rendering light and shadow that gave their works unprecedented depth and realism. Chiaroscuro, the dramatic contrast of light and dark, became a hallmark of Baroque painting. The Impressionists abandoned the studio for the outdoors, capturing the play of natural light on water, foliage, and stone. Photography is literally the writing of light, images formed by capturing photons on a sensitive surface. The word camera means room in Latin, referring to the camera obscura, a darkened chamber with a small hole that projects an inverted image of the outside world onto a wall. Photography translated this principle into a permanent record, freezing moments of light for future viewing. Cinema extended photography into motion, projecting sequences of images so rapidly that they appear to move. The flickering light of a movie projector creates the illusion of life, drawing audiences into stories told in light and shadow. The experience of sitting in a darkened theater, watching a beam of light paint images on a screen, remains one of the most powerful forms of storytelling ever devised. Architecture has long been concerned with the management of light. Windows, skylights, and courtyards bring natural light into buildings. The orientation of structures determines how sunlight enters and moves through spaces throughout the day. Gothic cathedrals are designed to fill with colored light from stained glass windows, creating an atmosphere of transcendence and awe. Modern architecture embraces glass and open plans, dissolving the boundary between inside and outside. Skyscrapers glow at night, their windows forming grids of light against the dark sky. Lighting designers shape the nocturnal appearance of buildings, highlighting features, creating moods, and transforming structures into beacons visible for miles. Light art uses illumination as a medium. Artists create installations that immerse viewers in fields of light, color, and shadow. James Turrell's sky spaces frame the sky itself as art, inviting contemplation of natural light and its changes. Olafur Eliasson's The Weather Project, a giant artificial sun installed in the Tate Modern, drew millions of visitors who lay on the floor and basked in its glow. The language of light pervades philosophy and science alike. The Enlightenment was named for its aspiration to illuminate human understanding through reason. Scientists speak of shedding light on problems, of bright ideas, of illuminating discoveries. The metaphor of light as knowledge runs so deep that it shapes how we think about thinking itself. And yet, light remains mysterious. Despite centuries of study, questions remain. The relationship between light and consciousness is poorly understood. We know how photons stimulate photoreceptors, how signals travel through the optic nerve, how the visual cortex processes patterns. But we do not know how these physical processes give rise to the subjective experience of seeing, the redness of red, the brightness of bright. The hard problem of consciousness, as philosophers call it, remains unsolved. Light connects us to the universe in ways both physical and emotional. The photons that enter your eyes come from sources near and far, from lamps and stars, from moments ago and eons past. Each photon is a messenger, carrying energy and information across space and time. When you see anything at all, you're receiving these messages, decoding them into the experience of vision. The atoms in your body were forged in stars that exploded long before the sun was born. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was cooked in the nuclear furnaces of ancient suns and scattered across the galaxy by supernova explosions. You are made of star stuff, assembled from atoms that once burned bright in the cores of distant stars. The light from those stars is still traveling through space. Some of it will never reach Earth, heading off into the void in other directions. Some of it arrived long ago, absorbed by surfaces, converted into heat, lost to the universe's steady increase in entropy. And some of it is arriving now, this very moment, photons that have journeyed for thousands or millions of years to end their travels in your eye. You're part of this cosmic flow of light. You absorb it, reflect it, and emit it. The warmth of your body radiates outward as infrared photons, carrying your heat into the room. The light that bounces off your face carries information about your appearance to anyone who looks at you. You are both a receiver and a transmitter, a node in the vast network of light that connects all things. In the darkness behind your closed eyes, there is still light. The spontaneous firing of neurons in your visual system produces faint patterns and flashes, the phosphenes that dance across your inner vision. Even in complete darkness, the brain generates the semblance of light. So accustomed is it to the presence of photons. And in dreams, light returns in full. The visual cortex, freed from the constraints of external input, creates images of extraordinary vividness and strangeness. Dream light is not real light, but it feels real. It illuminates worlds that exist only in the mind, revealing landscapes and faces and events that have no existence outside the dreamer's brain. Perhaps tonight you will dream of light. Perhaps you will walk through fields of sunlight, or float among stars, or watch a sunset that never ends. The light of dreams is a gift of the sleeping brain, a reminder that vision is not just reception, but creation. The world you see is assembled by your mind, constructed from photons and expectations and memories. In dreams, the construction continues, unmoored from the constraints of physics. As this journey through the quiet science of light draws to a close, let the facts and stories drift away like light through water, bending and softening and dissolving into the general glow of rest. You do not need to remember any of this. You do not need to hold on to anything. The light will still be there when you wake, faithful and constant, ready to show you the world once more. The universe is filled with light. It has been shining since the first moments after the Big Bang, when space itself became transparent and photons began their endless journeys. It will continue shining for trillions of years as stars burn and die and new stars form from their ashes. Light is woven into the fabric of existence, a fundamental feature of the cosmos, present everywhere and always. You are part of this luminous universe. The light that falls on your skin, that enters your eyes, that warms your room, is the same light that powers stars and reveals galaxies. The photons that surround you now are siblings of the photons that illuminate the farthest reaches of space. There is no special light, no ordinary light. There is only light, vast and various and everywhere. Tonight, as you rest, the light goes on. Stars are burning. Photons are traveling. The cosmic microwave background is washing over the earth, the faint echo of the universe's first light. Somewhere, a firefly is flashing in a summer meadow. Somewhere, a deep-sea creature is glowing in the eternal night of the abyss. Somewhere, a child is watching the sunrise for the first time, blinking in the golden glow of morning. And here, in this quiet place, you are at rest. The light in your room, whatever its source, is keeping you company. It asks nothing of you. It simply shines as light has shone since the beginning of time. Let your breath slow. Let your body relax into the surface beneath you. Let your thoughts soften and fade like the colors of a sunset, deepening into the velvet darkness of sleep. The light will wait for you. It will be there when you return. You are made of atoms forged in stars. You are warmed by the same energy that powers the sun. You see by the grace of photons that have traveled incredible distances to reach you. You are part of the story of light, a brief but beautiful chapter in a tale that spans the cosmos. If you happen to still be awake, you can go ahead and watch the next video now. But if your eyes are heavy, if sleep is near, then let it come. You have traveled far tonight, from the heart of stars to the back of your eye, from the Big Bang to the glow of your bedside lamp. It is time to rest. Sleep well, dream softly, and may the gentle light of the universe watch over you through the night. Good night.